Simulate your outcomes, electrify your designs, fabricate your visions, and explore the new possible.
Hello.
Yes, Mr. Verma, welcome. I think you are muted.
I'm unmuted now. You muted me.
Yeah. Yes, now it's on.
The Innovation Center, we're an end-to-end solution provider within Siemens. We're able to take a concept all the way to final implementation, all under one roof. So we saw the capabilities of the Markforged printers, and we saw the finished quality we get from the prints, the strength of the material, and we wanted to have a more industrial printer to be able to fast prototype and also potentially using it as a final tooling. When we first used the Markforged printers, a lot of people thought it would just be used for prototypes. And so there was an initial surprise by our end users that we were actually giving them a 3D printed part that they could actually use in the field or in a repair facility or manufacturing facility as the actual tool.
The major benefit of having the 3D printers in-house is that the time to develop an idea is dramatically shorter. Within a day or 2 days, we can go from an idea that we whiteboarded to a CAD model to a 3D printed part in our hands. So it drives the cycle time down as well.
The Markforged industrial printers act as a digital factory for us. In the past, you would have to make design decisions, do down selections during the design phase. We can now take 3 or 4 different designs, print them out, do the form function test, and then make a decision there which way to go forward. It just allows us to cut costs, and that money is realized back within the business units.
So with the Markforged 3D printer, we get great resolution on the parts. It looks like a real tool that you would buy from a store or something that would be in production.
So if there's an issue with one of the gas turbines out in the field and it has to go down, that means the lights go out or power has to come from somewhere else. So we developed this contoured cutback tool that allows the technicians to make a precise cut exactly where they need to. So this entire contoured cutback tool has been 3D printed. The only off-the-shelf components we had to use were some screws and the actual pneumatic spindle. We were printing this tool as a prototype, but we found that the Markforged carbon fiber composite material is actually robust enough to withstand field use. So we developed 4 kits that are deployed locally.
The Markforged printers have allowed our engineers to be more innovative by encouraging them to fail fast. It allows them to print multiple different designs, make changes to them without having to do that in a design space. And it allows them to get to a final solution quicker, to respond to these rapid prototypes that we have to develop for our business. With the additive manufacturing and the industrial Markforged printers that we're using, the sky's the limit.
Can I be seen on video?
No, Julie here, not weak, not you.
Yeah, because the host is not allowing me. You cannot start your video because the host has stopped it.
Olanes कशासाठी? Olanes कशासाठी?
Good afternoon, everybody. My name is Zuili Eclaire, and I am from Publish Industry India Private Limited. Publish Industry India is a 100% subsidiary of Publish Industry Verlag GmbH Germany that publishes the trade magazines A&D India Automation and Digitization and EM Efficient Manufacturing. I will be your host for today's summit, and it gives me great pleasure to welcome all of you with our technology partners, Autodesk Fusion 360 and Philips, to the summit, Virtual Additive Manufacturing Congress, Making Manufacturing Easier. AMSI, Additive Manufacturing Society of India, is our association partner for today's summit. The pace of additive manufacturing, which is AM or 3D printing innovation, is moving faster. With increasing global competition and changing global standards, manufacturers are becoming aware of the strength and potential of additive manufacturing in responding to market challenges and industry transformations and meeting tough performance standards. There is a continuous aim to bring down costs, achieve faster speed to market, and most importantly, reduce the impact of manufacturing on the environment, where AM plays a pivotal role. So today's Virtual Additive Manufacturing Congress will address common challenges, discover opportunities, and find ideas to accelerate the use of additive manufacturing. Our experts will also talk about AM for sustainable manufacturing, development of 3D printing applications, the impact of additive manufacturing on the supply chain, and lots more. So before we begin today's summit, I would like to give out a few instructions to our presenters so that the webinar can function smoothly without any hindrances. First of all, I request everyone to please check that your internet connection is stable. It's best if you're using wired LAN connection for a smoother connection with no issues. So you can make sure that the other tabs on your computer or mobile are closed. Please check that your web cameras are facing the light, so that you're facing light so that you are viewed properly by our audience. At the end of each presentation and the panel discussion and the fireside chat, we'll be open to Q&As. So if you look at the bottom of your laptop or your computer, then you will see a Q&A icon. So that is where you put your questions and we will have them answered for you. And I would request all the presenters to wrap up their addresses 2 to 3 minutes before their allotted time so that we have time for the Q&A. Now, let me take you through today's agenda. Our webinar will begin with the opening address by Dr. L. Jyotish Kumar, President, Additive Manufacturing Society of India. This will be followed by a technology presentation by Mr. Vipul Agarwal, Technical Specialist, Autodesk Fusion 360. It will then be time for the fireside chat. Then we'll have followed by the panel, which will be the panel discussion. So let's begin. Let's welcome Dr. L. Jyotish Kumar, President, Additive Manufacturing Society of India, to give the opening address. Dr. Kumar, over to you. Dr. Kumar? Yes.
In progress. Hello, am I audible to you all?
Yes, you're audible.
Yeah. Yeah, is my screen visible? Hello?
Yeah, it's visible.
Yeah, very good afternoon to all the dignitaries, all the speakers, all the experts, and all the participants who are there in today's Additive Manufacturing Congress, organized by EM and supported by AMSI and other industries and other experts. So I'm going to give a brief introduction about additive manufacturing, opportunities and challenges in India, what we are facing today, and what are the opportunities we can encash from the technology and apply and use it in each and every segment of manufacturing sector today, right? So it's good that Additive Manufacturing Congress and one of the other activities are keep happening in India. So, and we are all happy that, so a lot of things are happening in additive manufacturing. Also, most of the seminars and most of the webinars. And as of now, we all know that because of the pandemic, all the physical seminars or conferences or exhibitions are on hold. Hopefully it will get started soon. But anyway, the webinars are making us more active in this domain, and it's good So we feel that we're coming back to the normalcy of all these conferences, workshops, and seminars, at least through webinars. So I'll just focus on challenges and opportunities and challenges in India, what additive manufacturing is facing, and what sort of opportunities we can find. It's a brief introduction about our organization. It's a 10 years old society engaged in promotion of 3D printing technology, and it's creating an ecosystem in India with all the end users and also from the manufacturers of machines, materials, softwares. And we're also working with different industry segments, the defense, engineering, automotive, and so on. And we're also engaged in skill development and training activities, basically to help and empower India's manufacturing technology through additive manufacturing. We also publish journals and magazines. It's a bi-monthly one. And through our Center of Excellence, we're training industry professionals, engineers, and students. Some of the key dates, skip this, and it's our advisory board. Yeah, we have a small Center of Excellence in Bangalore, where we're doing the research and providing skill development and training for engineers, engineering students, and industry professionals. Yeah, we're also having various MOUs with the international bodies like 3D Printing Association in Korea, then French Rapid Prototyping Association, then Central Metallurgical Research and Developmental Institute, CMRD, Egypt, then with the German Consulate in India, with the British Deputy High Commission in Bangalore and India. So these are all some of the activities what we are engaged in. So to begin with, as we all know that, I'll start with additive manufacturing. We all know that additive manufacturing is a layer by layer fabrication of three-dimensional objects, which can be printed directly from a CAD data using various materials such as plastic, metal, ceramics, bioinks, and so on. It's also known by various names, such as 3D printing, layer manufacturing, rapid prototyping, advanced manufacturing, freeform fabrication, SFF, solid freeform fabrication, direct digital manufacturing. But there is a standard. As for the ASTM F42, the technological term is called as additive manufacturing, since the material is added in layers to build the final component. It's called as additive manufacturing. Yeah, some of the common types of additive manufacturing technologies are liquid-based, solid-based, and powder-based, and wire-fed. When I say liquid-based, the material will be in a liquid form. Some of the important technologies like stereolithography apparatus, polyjet, and so on. And the solid-based fused deposition modeling and so on, where the raw material will be in a wire form, plastic wire form. And the powder-based is some of the metal additive manufacturing, selective laser sintering, and selective laser sintering of nylon powder, and direct metal laser sintering, and so on. And also, when it comes to plastic powder bed blown powder, is a very advanced process called laser metal deposition. It's a very interesting field where it has got applications in most of the engineering industries, defense, automotive, aerospace. Not only printing the components, but also repairing the existing component, which is very important application point of view. But also, one more latest technology is called EBM, electron beam additive manufacturing, where the metal wire is fed and it's got melted and builds the component as per the CAD file. Yeah, the small announcement from AMSI, we are coming up with our 10th international conference on June 16th to 18th of December 2021 at BIEC Bangalore. For more details, please visit our website. Yeah, let's come to the point now. Opportunities and challenges in India. This is a very important point, and which helps us to think, adopt, and proceed further to nourish and nurture the additive manufacturing in India. Why we are not going ahead at the speed of smaller countries? For example, if we take Singapore, they are more advanced in additive manufacturing, but India being such a fast growing economical country, we're still struggling to adopt and take the benefit of the technology. Why it's happening? So what are the challenges and what are the opportunities we are facing it? So the first, let's focus on the opportunities. There are plenty of opportunities. For example, if you take the healthcare sector, you can fabricate or you can build biomedical implants, prosthetics, skins, tissues, and intricate organs. Of course, biomedical implants, there are so many industries. If you take, there is a company in Pune, they are very much focused on printing biomedical implants. They got various type of certifications, and they are focused on printing. And if you take Supercraft 3D in Bangalore, they're also doing wonderful jobs. They are printing implants and helping doctors and surgeons in the healthcare sectors. And also some of the hospitals in Bangalore, they are also started printing scaffolds for urology applications. That's also happening. And intricate parts, intricate organs. Some of them are printing heart tissues, liver tissues, and so on. So these are all the latest developments happening in healthcare sector, and there's ample of opportunities for additive manufacturing in this field. What we have to do is we have to look into it, do some research, and adopt the best practices from the Western countries, and adopt it how they are doing and what they are doing, and try to collaborate with them, and we have to proceed further. Yeah, the military. Yeah, then the military superiority. There's a lot of opportunities for additive manufacturing in military. The technological advancements in additive manufacturing, which has the potential to fortify India against military warfare, and in place of storing important stocks of military, so we only need to transport the specialized or what we call as the required additive manufacturing machine to the war field, and you can print the components which is needed in the war field itself, so that we can avoid importing of raw materials, and we can cut down the manufacturing processes cycle, and it helps to avoid the logical problems where in most of the places will not be able to reach during the military operations. So it has got a lot of opportunities in military superiority. Then electronics additive manufacturing adoption is growing drastically, and it's a fast growing field outside India. So there are various 3D printing machines which are printing semiconductors, which are printing on various types of electronic equipments. But in India, we're still opening up. We're just seeing what are the opportunities, what we can do. The best opportunities is that the Ministry of Electronics and Information Technology, Government of India, has made a strategic plans how we can adapt additive manufacturing to the maximum extent in India for electronic segments. So it will be useful for industries like automotive, defense, aerospace, medical devices, and so on. So this will also help us to create an ecosystem, self-reliant ecosystem for manufacturing of electronics items in India. Then the aerospace is already using most of the highly critical components with using super alloys such as titanium, chromium, cobalt, inconel, and so on. To the maximum extent, we need to adopt the best practices of additive manufacturing. So still we are lagging behind because of most of the advanced equipments are not available in India, and we are not able to install those because of various reasons. And this is a very big opportunity in aerospace field. So where we can do 70 to 80% of the components can be manufactured for final end use applications, not just for prototypes. We can use it for final end use applications, so that it will help us in the value chain, and we can also reduce the manufacturing time, and also to the maximum extent, the manufacturing cost of manufacturing will drastically come down, and also the lightweight components, highly critical components can be manufactured, which is going to be a very big opportunity for aerospace segment. And this will happen only when the government and the public sector join together, when they have strategic investments in this technology, and if they come forward jointly, and definitely we can make very big changes, and the technology is going to be a very big game changer. And the defense, of course, we all know that most of the DRDO labs, they are all using additive manufacturing today, but up to a certain extent. But we are not, in the direction where it's being used by other countries. So as for one of the report, India is currently the second largest importer of defense equipment. It imports by ordnance factory boards and defense public sector undertakings, which are estimated that to around 20,000 crores annually. So the importer of defense equipment to India is coming. It's not a small amount, 20,000 crores annually. So if we adapt additive manufacturing, the right technology, right machines, and the right applications, definitely we can control this import, and we can have self-reliant, and we can say that it's made in India and make in India, and it helps us to save most of the time, cost, and we'll be having a pride that these are the components, these are the defense equipments manufactured in India, and we can serve our nation. And the capital goods, of course, capital goods, most of the components such as textile machinery, earth moving, mining machinery, machine tools, heavy electrical equipment, printing machinery, food processing, they're all being manufactured today using additive manufacturing, and it's a great opportunity. And the consumer goods, as I told you, toys industry is going to become a very big market for Indian economy. In the jewelry, art, fashion products. When you say fashion products, the Korean people have to use additive manufacturing to the maximum extent. Because I was there in 2017 for one of the conference on 3D printing. Models have started using 3D printed dresses, and also 3D printed jewelry and 3D printed wall paints. It's a major business in South Korea. So these are the models and the opportunities which we have to tap and adapt the best practices from the world using the technology, and we can improve the manufacturing capability in India, and also to show the world that what we can do using the manufacturing process. And also construction and architecture, which is coming up and it's growing drastically. As we know that L&T, in collaboration with a company called Cobot, they have built an office space in one of the places in Tamil Nadu. They have built an office space within 3 days. 3 days. So you can see the drastical around 70 to 80% reduction in time and the cost, and the building was superb. I mean, these are the technological advancements and opportunities which is happening with 3D printing in construction. But also in most of the places, they are building bridges and toilets in 1 day. You can build a toilet in 1 day. So these are all the opportunities which we have to tap and make use of the technology to help us on the automotive field. Automotive field, as of now, around 35 to 40% of the components are being 3D printed. It could be plastic, metal, and where it's also reducing, helping us, reducing the import dependency, also reducing the cost. That's one thing. Also spare parts and cost is also reduced, and the cost of inventory is also reduced drastically. But again, we have to look into the higher end metal additive manufacturing systems or latest additive manufacturing machines and the softwares or the materials. We have to try to adopt to excel our manufacturing capability. Yeah, let's look into the challenges to adoption. Why we have not adopted additive manufacturing like other countries, and what are the challenges we're facing? Of course, there are a number of challenges, but I'll mention a few of them which are very critical and useful for us to know. The cost of equipment and material. Of course, even today, additive manufacturing in India is still evolving. It is not 100% grown. It's evolving. And why this technology is still evolving stage? Because of the material cost and the equipment cost. Most of the industrial grade additive manufacturing machines and materials, they have to be imported. And then it's being imported today, even today. This is also one of the reason. And the lack of formal standards. We don't have formal standards. We are using some of the ASTM standards as of now. And this is, creating big challenge for us. So where we are not able to use the 3D printed parts, even the components are much better than the conventional manufactured parts. Since we don't have a standard, it's stopping us somewhere to take the 3D manufactured components to the next level because we don't have proper standards. But somehow ASTM F42 standard is helping us at some places where it has standardized the process, the material, and applications. But it has to improve. It has to improve drastically, so that will help us to adapt the additive manufacturing process. Yeah, the lack of ecosystem. We have been trying. AMSA has been trying from past 10 years to build a positive ecosystem for additive manufacturing, but the phase what we are going is not. I myself personally not happy because various reasons. So if you see the service segments, the service providers in India, there only few of them are only few. Okay, where most of them are not having higher end machines. Some of them are having only the basic 3D printing machines, which is not capable of doing all the parts which is demanded by defense, aerospace, or automotive industries. So this is not a good environment or ecosystem what we have in India right now. And also monopoly of additive manufacturing market by foreign OEMs. Of course, even now today, only few companies are manufacturing plastic as well as metal machines. Some of the companies such as Integrity MLS or ACE, they have done a fantastic job in building made in India metal 3D printing machines with their own softwares. But this has to increase. And this is also one of the challenges what we are facing today. And also the biggest challenge with these machines, again, is the material. Most of the material even today being imported. If you take a titanium, for example, we have to import and we have to wait for months together to get it cleared in the customs and the heavy customs duty. And, some of the industries are there, attempting to develop these materials, and some of them already been developed. But again, we have to go to the maximum extent. Yeah, the cost of equipment and the material, as I mentioned to you, the cost of the material is high and the cost of the equipment is high. That is also one of the challenge in adoption of 3D printing technology to the maximum extent. Yeah. So another biggest challenge is that we don't have skilled manpower, lack of skilled manpower. The good thing is that these days, most of the universities and colleges, they are developing 3D curriculum in their studies, but it's limited to a certain stage. But what we need to do is that we have to develop skilled manpower to the maximum extent where they can print the component, where they can see the application in aerospace, defense, and automotive industry, where they can visualize, they can operate the software and print any final end-use part with the cost optimization, material reduction, and cutting down the time. So these are the things where we need to keep in mind and train the manpower. And in fact, we are working with US, Germany, and we just started Additive Minds program, and we have opened the Center of Excellence in Bangalore, and very soon we are opening up one in Mysore as well. So the main motive is that to prepare industry-ready engineers in additive manufacturing. So this will help us to address this problem and help us to create ecosystem with the skilled additive manufacturing engineers and manpower, and helps us to take it forward the additive manufacturing technology to the next level. So and also Government of India, Ministry of Electronics and Information Technology started a National Center for Additive Manufacturing in Telangana, and we are all working together to create an ecosystem, and where most of these problems will be addressed. And this is going to start very soon. It's one of the biggest project, and it's my dream project. I've been dreaming this for past 10 years. So hopefully now it's happening. And we hope so that India in coming days embraces the cutting edge additive manufacturing processes and use it for our various applications which we need it in defense, automotive, aerospace, healthcare, and so on. And we hope for the best. And I wish good luck for all the speakers. And thank you.
Thank you, Dr. Kumar, for joining us. That was indeed a very informative address where you spoke about the opportunities and challenges in India when it comes to AM, from the capital goods to the automotive sector and the challenges in adoption. So thank you so much for joining us. If you have any questions for Dr. Kumar, then please drop them in the Q&A box and we will have them answered for you. Thank you once again.
Thank you.
Yeah. Moving on now, ladies and gentlemen, we now have Mr. Vipul Agarwal, the Technical Specialist, Autodesk Fusion 360, giving us a technology presentation. So, Mr. Agarwal, over to you.
Thank you, Julie. So, hello everyone. I am Vipul Agarwal. I come from Autodesk, and what I have is a technology presentation in which we will talk about the software tools in additive manufacturing. Okay, so as Mr. Jyotish Kumar showed us that there are many methods in additive and even more materials which we can do additive manufacturing with, but still we are looking for the best practices and learning the best practices and adopting it in India. Right. So in these terms, what if I say that let's do it with the software or the tools which we have got in the software. So here I'll be showing you a few technologies which will be helpful for you whenever you are doing additive manufacturing. Okay, so the three technologies which I'll be talking about is, first one is the parametric mesh modeling. So parametric mesh modeling, anybody of you, anyone from you, if you have dealt with STL files, you must be knowing what is the pain of working with STL files. Right, you cannot do anything. The editing is very tough. The repairing is very tough. And while transferring the mesh files from one PC to another through a mail or something else, it becomes distorted, and then you have to redo everything. So we'll be talking first about the parametric mesh modeling, how we can help you, how things work in a software. The second one will be on the additive printing side. So actually, as we told, like the trained labor is one of the challenge which is there. But what if I say that the design person he is also responsible for doing the designing and manufacturing, and he can do the printing by himself. There is no need of trained labor. He can check what time it is going to take, what supports is needed. If you do X type of support, then what will be the consequences and everything. So that we will see in additive printing. And third one is on the generative design side. So let's say designing itself, since additive has opened up a wide space in the designing industry, that you can do designing to an extent where it was not possible to manufacture in conventional methods. There is a gap which we can clearly see where you are not using the design potential to its extent. Okay, and for the same thing, we have generative design, in which there will be multiple optimized solutions, multiple optimized designs which will be coming out, and you can compare the best designs out of it and take it to additive manufacturing. So this is what we are going to see right now in the next 20 minutes, and let's start with that. So first one is parametric mesh modeling. So as we discussed parametric mesh modeling, this is a sample of mesh file which you might get a sample of how the mesh files look, and the repairing of this is very tough. So you can see this is like an unwanted area which I have, and there is like this thin line which needs to be flattened. So if you want to do it, it becomes very clumsy. But with the mesh modeling techniques in Fusion 360, it can be done very easily, right? The second one is closing any loops which might occur while transferring the files, any errors which might occur. So you see, with just a few clicks, we are able to do it. The commands are made in such a way that it will repair the files with the existing existing design criteria which has already been taken, right? Even for repairing, flattening the places, this, if you see this, even this small bump in the design will cost you a lot more while actually manufacturing it. And if you consider the design, this is not needed. So this is like an extra layer, but editing it makes very difficult. But with the parametric mesh technology, you can see how easily it can be done by just selecting it, giving it the flatness, and done. Okay. For example, if I want to take references from a design, if I want to take an exhaust, build an exhaust system from this engine, but the file is in mesh, I cannot take references. But again, with the parametric mesh modeling, you can actually take the section of it and then start modeling, which further can be taken into made into a complete model, something like this, right? The next thing which we will talk about is actually on the additive manufacturing side. So once, let's say, the model has been prepared, how do we check that what kind of settings will be good for my printing? What kind of settings should be adopted? How to optimize it? What are the best practices? So we have a manufacturing environment integrated with Fusion 360, which actually is very much useful to do all kind of activities. Considering this example, I can quickly hop on to the manufacturing environment from the design environment. And then there is an additive tab specially mentioned for it. We can start with a setup in which we actually define which machine I am going to use. There are a set of machines which has been already developed and provided in the libraries. You can create your own machines, giving it the dimensions you have, the extruder configuration you have, and all those settings. Once the machine has been taken and created, okay, you can select the post processor which you will be using to take out the post. So basically what we will be doing is, after doing all the settings, we'll be taking out the G code M codes and putting it into the machine to print. So I can do this at this place itself. Once this is done, what I'll do is setting up the part into the table. So that's again not a no problem for me. Everything is automated. I just need to do one tick and you will be able to see that the part is kept inside the table. Now the next one is a very important aspect in which I need to check by which configuration I'll get less amount of support structures. So how do I intelligently orient it? But why should I think of it? Let's let the software do it for us. So there is an option called automatic orientation, which will actually take inputs from you, like how much is the extent of your project, how much you can take it up, and what is the ranking which you will be giving on the, sorry, I just did it a little bit more. So what is the importance of the ranking which you are giving? So if I need very less support volume, I can give it a ranking very high. If I want like low bounding box volume, I can give that as very high. And what it will do is it will give me suggestions according to that. So if I see the orientation details, it has given me around 14 suggestions. This is the first one. This is the fourth one. And you can also go ahead and view what is the support area and support volume. The first one is with the least support area, support volume, means whatever I have given the priority, and going down, it will actually decrease. So I can select any one of it and go ahead. Okay. Further down, for the machines which we have created the library, we support the print settings. Again, these print settings are the industry standard print settings which has been given, which that specific manufacturing machine and that specific manufacturing machine company suggests you. Okay, so here you can do the basic settings, give the settings what is done, change something in the basic settings what has been given. If you are using some machine which you have created in Fusion, then you can define all these things by your own. Once defined, it gets stored in the template. You don't need to do it again and again, and everything is like systematic and in a flow from next time. Once this is done, the last thing is how we do want our infill. So infill is like one of the things which is very important in Fusion 360. Sorry, very important in additive manufacturing because it decides the weight and the strength of the part finally. Oops. So it decides the weight and strength of the part. So what we can do is with the infill settings, let me bring it back somewhere here. So we have all the types of infills which are getting used. You can see it in this menu. Again, taking the best practices from other countries. These are the infills which everybody is using in the industry. You don't need to think much on it. You just can select the structure and go ahead with it. Okay, even in this place, what you can do is with multiple infills, you can try out which will take the least time to print, or let's say which will have the best printing quality, whatever you prefer. So you can work with whole lot of ranges, and through that you can compare your final products and the pricing accordingly. So let's say if you want to concentrate on price, you can make the infill a little bit low. If you want to concentrate on the quality, you can make the infill a little bit more. Finally, I can generate the toolpath, and what it will do is actually divide everything into layers with the infills and do all the settings. Once this is done, what I can do is I can view what is the printing time, so that further if I need to quote anyone or I need to check how much it is, and also simulate and see it how it will be doing. So here you can see on the right hand side tab, it's saying that the layers will be 500, the current height at 0.2, 0.3, and so on and so forth. It also is color coded. So the green ones you are seeing are supports. Now the infills has started with the red ones. Sorry. And the inner green layer is actually the part boundary. Right. So this is how you can easily print it, and then further take the NC code, save it in a program. There are a whole lot of set of additive post processors which are there according to your machine, related to your machine. And what you can do is actually take this post processor to your machine and print it. Everything is done automatically through the software. It's just you give the inputs and it will give you what you need. Right? There are many libraries. You can also export it and save it with others. Here is how you can view the printers, make your own. Every setting is done. Right? Then the third one is generative design. So what if I told you there is a way, if you give the inputs on what are the end conditions and what is that you want to achieve from it, it will give you a design which will be manufacturable. Right. So that is what generative technology is. Generative design technology is. It is going to intelligently tell you what designs you can make, and not it wouldn't give you just one design, but a whole lot of designs to choose from. Okay. Here, let's see how generative design works. The first thing is, let's considering this bike and I want to make the connecting of this rod. What I need to do is give it the end conditions. So this is the end conditions where everything is going to fit. Okay, I'll go into the generative design workspace, define this end conditions as that this is where all the fixing should be happening. Give it the constraints, so where I want to fix it. Give it the loadings. There are all the types of loadings available in this. Sorry. Yeah, give it the types of loadings which is there. There are numerous types of loadings which are available. You can select the loadings, force, pressure, and everything. You can give it the objectives, like what objectives you want to achieve. You want to have a factor of safety of 2 or more. You want to make it as like that it can go for minimum 15 hertz of modal frequencies, or even displacement, like how much displacement it could take place. So all these things, and then further giving the manufacturing criteria. So you can give here the production volume you want to make, what all manufacturing technologies you are using. I can also select other manufacturing technologies just to see that, okay, can this be cheaper in a VMC, or can this be cheaper in a 2-axis cutting? And then go ahead and do the study. It usually takes some time to do the study, and then these are the kind of results it will give you. You can differentiate between the studies with the filters and see the data in a graphical form. Okay, arrange the data in whatever factor you consider most important, maybe volume, mass, or you want the factor of safety to be important, or maybe the estimated manufacturing cost. Okay, so we use our partner a priori on defining the manufacturing cost for these items, and then select the appropriate results or a range of results which I need, and then compare those results inside Fusion itself. So you can see this is the range of cost it has given. I can make the graphs of how the costing is taking place, and then find a point where actually my cost is merging and take the decisions accordingly, right? And this design, again, you can take out as a parametric form, and if you feel any changes is needed, you can do it manually and then use this design again. Go ahead and manufacture it however you want it to be, either milling, turning, additive, whatever it is. So this is the overall technology which are there in the industry from Autodesk side. Just a gist of it, how it works and what it can do. Okay. We have other technologies as well. If you have any question and answer, we can take up the question and answers now.
Thank you, Mr. Vipul. That was indeed a very interesting presentation where you talked about these three technologies very broadly about parametric, mesh modeling, additive printing, and generative design. So before we actually, audience, move on to the Q&A, we have a video by Autodesk for you. No, actually, before that, we have a poll for you. So can you please have the poll on screen by Autodesk?
So we would like to know, how did you feel about these technologies? Do you think that this will be any useful for you?
So you have 15 seconds to vote for the poll. Was this presentation useful for you? Extreme, average, less? So you can go ahead and vote. All right, so can we have the results for the poll? So 64% have said that it was extremely useful for them, and 31% have said it was an average, and 5% have voted for less. So we have got the maximum for extreme. So that's a good result. So now, yeah.
Yes, before moving forward, if you feel that you want to contact Autodesk to know more about these technologies, here is our contact information.
Yes. Yes, you can get in touch with Autodesk through this contact information that has been given you on your screen. And now we have a video by Autodesk for you. So can we please have the video played?
Innovation. It's never achieved alone. It took two intrepid brothers to push us into the air. Two visionaries competing to electrify the world. It took a team of thousands to launch us into space. We collaborate. We share ideas. We push each other to be better, move quicker, and solve problems we don't know exist yet. We explore and iterate through endless possibilities. We prototype, we fail, and we succeed with rigor. We're designers, engineers, machinists, fabricators, inventors, and doers. Our curiosity leads us to imagine new possibilities, expand our horizons, and explore the unknown. But to succeed, our tools need to be up to the task. Having the right design, simulation, and fabrication tools is essential when bringing an idea to life. Imagine the opportunities when you bring these tools together on one platform. With Fusion 360, you can control your data, drive your machines, simulate your outcomes, electrify your designs, fabricate your visions, and explore the new possible.
So that was the video by Autodesk for you, ladies and gentlemen. Now I would like to call Mr. Shekhar Jutkar, the Chief Editor at Publish Industry India, to please ask Mr. Vipul if we, for any questions that we have from our audience on the presentation. So Mr. Jutkar, over to you.
Yeah, sure. Thanks, Julie. Yeah, thanks, Vipul. It was a really good presentation. You gave a lot of insights which are very easy to understand and very practical info it was. There is one question. How is the Autodesk software different than the materialized magics?
So materialized magics you're talking about.
Yes.
So here in Fusion 360 Autodesk software, it's an integrated software. Whatever the three interfaces I showed you, three technologies I showed you comes inside one. And also we have the conventional designing and methodologies as well. So where other softwares might be limited to one specific use case, here is like the whole area which you are getting. And even I can say about the mesh working is like really awesome, and it's very much handy and easy to use related to it.
Okay. There is one question from the student. How to earn legit Autodesk certification? Can you please provide any voucher for that?
Yeah, so if you go into autodesk.com or like just go into fusion360.com, there is a student section in there, and you can obviously log in into there, and then there are many courses through that you can get the certification done.
Okay. Then what is the advantage compared from the Creo lattice structure design?
So when we consider it with the lattice structure designing, it's mostly just the designing aspect and not the printing. So further you might need to get that into a third-party software or the actual 3D printer software and do the printing. While in this case, you could see the latticing, the infill and everything is done inside Fusion, and you can directly push it to the machine with the G-code inputs. So it's more smooth interaction in here.
Okay. Yeah, I think other questions you have already answered on the Q&A box.
Sure.
Yeah. Okay. Thanks, people.
Thank you, everyone. Thanks.
Thank you, gentlemen. Ladies and gentlemen, it's now time for the fireside chat. I would like to welcome Mr. Surendra Vaidya, EVP and Business Head, Godrej Aerospace, and Dr. Deepa Srinivasan, Chief Engineer, Pratt & Whitney, United Technology Corporation. I would also like to ask Mr. Shekhar Jutkar, who was just with us, to please join us again and start the fireside chat. So, Mr. Jutkar, over to you.
Yeah, sure. Thanks. Yeah, sorry for the little delay, but we'll try to recover it in our next sessions. I'm happy to welcome our esteemed speakers today of today's session, the Fireside Chat, Mr. Surendra Vaidya and Dr. Deepa Srinivasan. Uh, there is always the question that whenever any new technology comes in, whether it will replace the conventional technology. So in case of additive manufacturing also, the question is whether it will replace this conventional manufacturing. I recently came across a research report which predicts the additive manufacturing market reaching about more than $51 billion within a decade. So you can imagine there is a definitely huge potential in this. But it would be interesting to understand and analyze on the role of additive manufacturing technology in the future of manufacturing and how strategies and business models will evolve further with this. So we will discuss this and other things in our session today. With this, I would like to start with Mr. Vaidya. So you, Mr. Vaidya, you have been working in the manufacturing industry and aerospace sector in particular for a very long time. So how do you see the acceptance and use of additive manufacturing technology in the aerospace sector? Do you see any challenges in it?
Thank you, Shekhar. I hope that I'm audible.
Yes, yes, you are audible.
Okay. Hi, Deepa. Good to see you after a long time and get connected through this congress. I think you have asked a very important question as how the aerospace looks at it and why there is a need for aerospace to really invent this technology and bring it. I will give from a manufacturing perspective, but I think Deepa is going to give us very detailed from the engine manufacturing. And fortunately, I have engine background at the backdrop of my picture. I mean, just to give you that there are a number of materials, number of parts which consists this particular engine. And if you have to manufacture each part with the current process of the subtractive manufacturing, normally we start with about 10 kilograms of material, and finally the part which comes out is sometimes not even 1 kg. So it is 90% of the material you need to remove from a very costly, expensive forging or material which just now, Mr. Dr. Kumar explained that in aerospace, we have very exotic alloys like titanium and Cornell, which are very, very expensive and not easily available. And very few industries really know how to make them to the perfection. Now, in such scenario, if we need to really apply this 3D printing technology, which is additive technology, where the ratio of what you are going to consume as your input material to the final product will be maximum 10% or 15%. I mean, there will be some machining which is unavoidable in aerospace because of the tolerances and the demanding requirements which it's going to bring in. So that's why aerospace considers this as a very, very important technology from the point of view of the economics to save on the raw material, which is becoming expensive and expensive. And right now you must be seeing after the COVID, the commodities are going up like a sky high, and then maintaining your the raw material prices or the BOM cost itself has become a real challenge. And over and above that, if you have to spend additional machining, I mean, when I say that 70-80% of the material has to be removed, I mean, indirectly, I'm saying that those many hours you have to spend to really get that part. So not only the material is expensive, but the manufacturing technology also becomes expensive. So that's the way we look at it at the aerospace. However, I would just, before closing or before I finish the answer to this particular question, let me give the background. I mean, why the aerospace is so particular about these kind of a demanding materials or the exotic materials. I mean, just to take a simple example of the civil aviation aircraft, when we sit at it at any of the airports in India, maybe the temperature will go plus 50 degrees in Rajasthan to minus 20 degrees in Kashmir or something like that. But when it is going to fly at 30,000 feet, you will always see outside temperature of not more than minus 30 degrees to minus 50 degrees centigrade. So that means in a short while, a material is going to see a terrible shock from minus 20 degree to minus 50, or in the extreme case, plus 50 degree to minus 50 degree. And that kind of a temperature in just few minutes to reach up to that height is something which is important. Secondly, I think the kind of materials, that is the fuel and the oxidizers what we use, that is also very, very corrosive in nature and requires a particular attention or a particular material. The third is all these engines or all these aircrafts, when we are going to sit into it, it's unlike any other two-wheeler or a four-wheeler or any other automotive or locomotive, where you have a chance to at least attempt to repair. Here, there is no chance to repair. So you have to be perfect at the first place itself. And that is where there are large number of codes, regulations, specifications have been laid down. And the agencies like in India, we have DGCA, DGAQS, MLAC, those have been came forward to put the restrictions, and they strictly monitor that for every flight, whether the data which is mandatory to be reported to them has happened, and then only the flight clearance is being obtained. And I mean, this background, I thought that will be more important. And with this, I will stop with this answer. I mean, I don't want to take the entire time in the first question itself, but there is a lot to discuss in aerospace.
Yes, there are more questions coming in.
Yeah.
Yeah, but do you think because of these challenges which we have in the aerospace sector in particular, so additive manufacturing will have more kind of like huge acceptance in future to overcome these kind of challenges?
Yes, I mean, it has a potential. Now that potential, has it been fully tapped? I will definitely say no. I mean, there are many processes which are required after you do the 3D printing.
Correct.
There is a sintering which is required. Then you have hot isostatic pressing in certain cases. Then you need to ensure that you get the right kind of grain orientation, or you get the right grain size. Then you must have that kind of a purity when you are going to do it. Unless you have a EV welding, a titanium kind of a material will be very difficult to fuse because it is having very high oxidation. So if you do it using a conventional process, and if you don't protect it, you may be able to develop a part, but with the titanium having oxidized, it drastically reduces its properties as well as the corrosion resistance. So the benefit what you are going to get will be completely lost. So, I mean, there are a few challenges also which are being seen, but I don't really see that the 3D printing we should really consider as a replacement. Like when the CNC machines came up, we were very thrilled. Okay, oh, so today the manual operators, they were, I mean, the skilled managing both hands to really give the required profile, or do the left-hand side, he was turning one knob, right-hand side, he was turning another knob. And what will happen? He has to stop in between, think again, do the resetting of the equipment. Or when we moved from 3-axis to 5-axis, I don't think that the additive manufacturing should be looked as a simple, I mean, an incremental increase in the machining. The additive manufacturing has far beyond potential. I mean, today, ideally, as you see the background, I have chosen this background only to elaborate that there is a blue color, there is a white color, there is a black color. I mean, these are all the different materials. That's the way we are choosing it. But if I have a choice as a designer or as a metallurgist, if I want to really choose a particular material as a combination of 2 or 3, that is something which is not possible today. I mean, unless you have a friction welding kind of capabilities. I mean, using aluminum with stainless steel or titanium with stainless steel is something which is impossible today. But 3D printing has that potential. You can select a barrier layer, and while you are printing a part, that time itself, the core, like for giving a, I mean, much easier example, if I want to create a knife, which will be very hard, but should not give a corrosion. Typically a knife what we buy in the market, which is very hard, but made out of some blade or X something. If you don't dry it out and keep it properly within before the next usage in 2-3 hours, it will have a corrosion. So I need to do some chrome plating, or I need to do some different alloy like stainless steel or some precipitation hardening steels or something like that. So that it will give the hardness. At the same time, it will give the corrosion resistance. But then the cost is going to go up because I'm going to do it completely out of that costly alloy. So I look really 3D printing where we'll be able to do a combination of material. That means the core I will print in carbon steel, but when I'm coming to the outer shape or the outer the layers, I will use a stainless steel. So it will have a combination of hardness. It will have a combination of stainless steel. And similarly in the design, I mean, we'll listen surely from Deepa more, but if I take an example of an aircraft engine burner, the burner is made out of minimum 15 parts. Then only your fuel injection burner is ready. Now 15 parts, if you are going to make separately, 15 different tolerances to be achieved, 15 different assemblies to be made. Every assembly has to be perfect. Otherwise you have to do match assemblies to achieve that kind of accuracies in the flow rates and uniformity in the flow rates. but the same thing can be converted 15 parts into one single part, and then the ease of manufacturing will really come. So I look 3D printing as not an extension of the machining process, but really a technology changeover where the multiple combination of materials can be added into one part and the number of parts can be reduced down to only one part. And these two examples will give the designers far, far better flexibility once we stabilize this process. And then I would think the optimization of all the aerospace industry will take place. I mean, today we are very, very expensive. That's because the rules and regulations are preventing us to do that. But if we, keep the rules and regulations same, but adopt these newer technologies, I think we can really bring down the cost to a great substantial extent.
Perfect. Yeah, Dr. Deepa, you are in the R&D. You are working in R&D profession for long, and you are also the inventor and the developer of several new technologies, having many patents as well. So, can you highlight some of the emerging trends and the new applications in additive manufacturing, which the manufacturing industry can get benefited from now and also in the next few years?
Sure. First of all, thanks for having me over. A pleasure, like Surendra said, to be able to meet everybody virtually. I think it's been tried in the last 4 or 5 years at least. There's a huge awareness for all the performance matrices that he so nicely highlighted, simplification of parts, and then where it is still a low volume process. So if we look at specifically advances, I think in the last couple of years where I've been tracking is in multi-materials. Until about 2-3 years ago, we were still working with very popular alloys. Also, we were looking at, people were saying in the entire cross section that he has a beautiful backdrop of, we were not having 3 different colors. We were having shades of white, shades of, the same dark blue, and, black is black. So now the last, at least 3 years, I see that notwithstanding COVID lockdowns, a number of companies making powders or wires is it's just boomerang like that. So that is one of the areas where advances, at least I see. Composite materials also, there are a couple of players all over the world who have marched ahead. Then ceramic materials, this is another thing in terms of advances I'm talking about. And I'll start with material advances and I'll go to machinery advances. The other thing is also hybrid manufacturing. So I think these 3 or 4 areas where emphasis is being made in terms of an R&D worldwide, both at industry as well as national labs, as well as academic institutions. In terms of machinery, I think, again, I'll start with hybrid. People are looking with, if you're combining a number of parts, how can you do post-processing in one go? Build a few, I think Vipul, the previous speaker, also mentioned about making judicious use of the STL files and making sure of precision. There's a lot of advances in software. I see advances also in in situ defect monitoring. I think NDT is an area, non-destructive evaluation, which is still a long way to catch up for additive production parts. So in terms of even the build volumes right now. So there's a lot of work going on in terms of advances there, world over. And of course, people are also talking of multiple lasers and electron beams, combination of laser with even cold spray. Those are the areas where advances, at least I'm looking at it from the state of the art. Of course, inspection is a big place where, melt pool monitoring, in situ defect detection, smart optical sensors, etc. Those are where it is marching ahead now.
Perfect. Mr. Vaidya, in the manufacturing industry, there is always this continuous aim to bring down cost, then achieve faster speed to market, and most importantly, this reduce the impact of manufacturing on the environment. So how can additive manufacturing technology will play an important role in this area?
Yeah, as you see that any part or any innovation which has to be brought in to the market, first you need to do lots of protos and do a lot of lab tests before you can launch it into the market. Now, a typical time for auto industry, what I know is about 6 months to more than a year. And that happens because you require that much time to develop new tools and all the lines which are required. And similarly, in other industries also, it is the same. I mean, aerospace is the extreme where any new engine or any new aircraft takes about 8 to 10 years. And number of trials and modifications are required based upon the ground test what you do. So for each one of them, if you have to really make a different tool and a different the machining processes to be designed, it's going to take a very longer time. So it saves on time if you go for a 3D printing. It saves on, as I said, instead of having more number of parts, you can really make it out of the shorter number of parts. So your BOM becomes something which is very easy to manage. The third important point in 3D printing is that as you saw that any product, I mean, if you have to really make it, you require sheets, plates, tubes, maybe some forgings, castings, and different extrusions and different forms in which you will require the material to be procured. Now in 3D printing, you require to procure only a different combination of wires or the powders. And from there, you can print any kind of thing. The only restriction or limitation as we are seeing it today is that the number of powders or the size of the powders or the purity of the powders or the wires is limited. But of course, as the technology gets established and more popular, the raw materials will also start improving their availability and the spectrum of the wires and the powders which are going to come. The second is the size of the machines. The 3D printing size is also currently limited, and there are many applications which are going beyond 1 meter, and beyond 1 meter machines are really very expensive as on date. And when compared to the current way of manufacturing, if you have to spend so much of time and money into this the large size machines, then it is probably will not be able to compete with the numbers which are required. So you have to then put multiple such machines. So how are we really going to use this technology by maybe slicing large components into the smaller pieces, but making them to join in such a way that when assembled together, it will form as a single piece. And then many of these shortcomings which I just highlighted can be overcome. So that's the way I look at it.
Yeah, I think after analyzing the potential and what kind of challenges we may face, and also from the manufacturing point of view to bring down the cost and reducing the impact of environment. Now let's go some more into the deeper lines. Like I will then come to Dr. Deepa again, because since you have been in the R&D, so this question will be quite apt for you. So building to additive manufacturing reliability, that requires examining each step of the process for reproducibility and repeatability. So what do you think are the key factors and approaches to optimize each step to achieve the consistency in the production?
It's a great question, and also something very close to my heart. So, I may take longer than the time you give me for this. Actually, it is quite, it is, what I see is a lot of people are just jumping into the bandwagon because they don't want to feel left out. That is very good, because at least it will build those people who are set up, small SMEs in this area. At least there are at least 15, 16 service providers who are there all over India now. At least I'm sure there are many more which I don't know of. So the ecosystem to grow, you need a bit of both. But what happens when you jump into the bandwagon without due diligence done in any area is that you don't move very far. I'm talking of including the my own company, as well as people I've seen in several sectors, tool and die, automotive, healthcare, aerospace, space. Everybody is running into it, but if you don't do the homework, and it's not difficult to do the homework, because the beauty of additive is we do have a benchmark. We have a benchmark in the conventional process. The design may be slightly different, but people think we don't have ASTM standards. We don't have all the we do have some benchmark, even if you're replacing the alloy. I mean, so I beg to differ there, saying all you have to do is to make sure it is equivalent to, or if not, And the changing the design here is, that's the beauty of additive. I'm going to take one line and speak on Surendra's behalf, because where you asked, no, where can you cut down, where is it going to? So the whole point is not in not being able to wastage. You mentioned the previous question. I think here you can make the part with design for additive manufacturing. What is he mentioned, 10 kgs, 1 kg, you know, you can make it to 2 kgs to start with. Of course, you can't avoid machining. So the repeatability, reproducibility issues, 4 years ago, if you'd asked me, there were not that much of data available all over the world to share. And everybody was starting with a coupon level test. Today, we don't need to do, at least in the popular, about 20, 30 alloys that are being bandied around, maybe more, maybe 30, 40 alloys. We really don't need that coupon level test. You straight away start with the design criteria. But the fact of the matter is, design engineers straight away go and do the DFAM and manufacture it without bothering about this due diligence part in the beginning. So all I'm saying is, in a month's time, not more than that, 3 to 4 weeks, as much as you will evaluate the powder machine, the process parameters, you do your actual part. And if it is a high temperature application, or is it a wear application, is it a creep, is it, I don't know, whatever it is, do it in tandem, I'm saying. Thereby, the cycle time, he mentioned it several years to actually qualify an aerospace part. That whole thing can be cut short now in terms of reproducibility. And from the 5th week, you're starting to do reproducibility. That means if you increase the number of parts or the coupons in the build plate, then the heat transfer, what are the challenges you face during the reproducibility? Let's say a creep result is not repeating itself, it upfront rather than after 5-6 weeks, so absolutely important for the reproducibility of the part. But, the confidence level with which you build your data, this whole cycle can be shortened right now. And that is how, at least in the past, we've been able to get many parts out there. And of course, there are challenges, in which case, in the rotating part, if even after 2-3 years, you're not able to meet the creep requirement, you don't need 2-3 years. I'm saying with the knowledge between the metallurgy and the whole world, I'm saying we have enough knowledge now on several parts, several alloys, let me put it that way, that we can build prognostic analytical tools. I'm not even talking of constitutive or first principles modeling here. We are not there yet in additive. It is too complex. I'm only talking of, data-driven analytical tools can be built to say this is the factor of safety, just like we've been doing for conventional manufacturing. So I am really optimistic on that note, but by and large, what 80% of the people are doing is build coupons, do the testing. That is really old now, considering the speed at which we would like additive to be adopted for low volume processes, for unique, geometries, use and throw kind of, like, for example, ISRO, NASA, there's all low volume, one-time design for a particular cryo engine or something. Just adopt it, without too much of reproducibility. At the same time, for a turbine blade, such as what his picture is showing, yes, you really need to wait. You need to make sure repeatability is there. And some of the alloys may not even, he mentioned hipping. Hipping is probably good, but the kind of completely different, non-equilibrium conditions that additive gives to you, then maybe there you need to spend a number of years for some of the materials, like very difficult to weld materials he mentioned. Maram 247 is one of them. That'll never go up until you prove any amount of hipping. It'll be fraught with sort of suspicion. So there's a little bit of both, and adaptability depends on. I'll jump ahead and say we just need to choose the low-hanging fruit here. For example, one of the areas where I have always looked at metallurgically and design perspective is in repair of turbine components, repair of automotive components, hybrid manufacturing, conventional and additive, even for the tool and die automotive. You have a titanium alloy which is wrought. I think Mr. Vaidya has tons of it. They're experts in it. And then choose a particular part where a wrought and a hybrid can go in easily. to look at the performance of that particular product. So you have the best of both. He mentioned cast iron as an example. Yeah.
Right. Yeah, I will come to the last question, which I would like to ask to both of you, and which is very important in today's condition, and where the additive manufacturing is like people want to do it, but somehow there is some hesitation, there is some confusion, maybe because of not enough information is available. So I will start with Mr. Vaidya. How to develop an additive manufacturing strategy, and like convince probably the top management, or convince any corporate or any manufacturing company that why you need it.
So in my opinion, there are factors which we need to really look into it before we can give a proposal to our top management to really invest into it. First of all, we must select the right machine, the size of the machine, the specifications of the machines, typically like we have in machining the least count, and what kind of axis moments you want, so that your complex shapes and profiles you will be able to really get it through the 3D printing. The second is, I think we must have a good control from where we are going to have sourcing of our input material, either a wire form or the powder form. Today, both of them are not produced in India, and everything is imported, very expensive, available in limited quantities. You cannot really buy in larger quantities as on date. I'm not talking about the conventional materials which are available. I'm specifically about the aerospace and defense. It has that kind of nature. The third important factor is, will we be able to maintain the kind of environment this particular process requires? That is very, very critical, very important for the exotic alloys like titanium and Inconel. The cleanliness, the dust-free enclosure, which is important for having this. But these are not very easy. Here, when we are doing a subtractive machining, it is something which we cannot add into it. Even if it is very dusty, you cannot add any material into it. But when you are printing, you are melting and trying to fuse. So if any dust or any moisture or anything goes along with it, it is going to remain in that product permanently. So then it becomes difficult. So how are we going to really look into the environment, and what is going to be the cost of maintaining that environment, maintaining a dust-free enclosures or the dry rooms is not that very easy. And the last is, do we have really adequate non-destructive technologies in-house so that you will be able to give the reliability? Since it is having its own limitation, every part is casted and melted, and it's like a casting, very difficult to give a reliability than from a raw material. If you take a plate, from any corner of the plate, you take a sample and test it out, the entire plate, the technology has been perfected to such a level that it will be uniform only. But today you are very, very difficult unless you have a lot of reliability. But to overcome all these things, the reliability, I think the IoT, the Internet of Things, or the Industry 4.0, the various sensors which have come up into the market, I think those are going to revolutionize this 3D printing technology and bring in the reliability. Plus, I think the NDT in situ, that means as you are printing, you are able to do NDT, at least some of the X-rays or ultrasonics, to find out that up to what layer you have done and what layer it is sound to go ahead. Like in a welding of a thick plates, when you do it, you do take radiography or ultrasonic after filling up. Typically a 200 millimeter thick plate, you weld first maybe 5 millimeters or 10 millimeters and ensure that your root is properly fused, and then you deposit maybe another 20-40 millimeters, and then once again take a radiography. Then after making a 200 millimeter welding and then finding that there was a defect at 20 millimeters or 40 millimeters, and once again digging it out, is very, very, very difficult and costly. So I think this 3D printing is now becoming very easy to take care of it. So I think these are the measures. If we take it, I think we'll be able to easily justify. Plus the economics, as we discussed, I'm not repeating. I mean, ease of doing it, faster realization of your products, less number of parts. So your mind to market will be far earlier than what a conventional process can give.
Right, Dr. Deepa, you have any comments on this?
On the strategy part, is that right? That's a question.
Yes. How to develop an additive manufacturing strategy?
Yeah, sure. I think every sector would would like to adopt it. And the way I'll just take a leaf out of how we have done it in the aerospace is to look at the ROI. I mean, there is, there's no need where conventional is working really well. There is absolutely no need to replace. Obviously, I can't make a huge rotor. There is no great advantage in making a big rotor with something like that. Look at the business ROI, where it makes sense, where it can be adopted quickly. So I did mention to you that repair is one very strong area, including if you look at some of the flying parts, repair has been a great location, because they're getting small volumes to replace them to the net shape, print, paper to print is difficult. So I think each business, for example, tool and die, let me take, I think there's a huge potential there waiting to be untapped. Healthcare sector, yes, notwithstanding the cost, I think everybody has to find their niche area of the business case. And it's very easy also. Even yesterday, I had a group from another, colleagues from another business in our own company who came and asked. I said, it's just much easier to look at it. Right now, what everybody is doing is driven by the need to actually, I need to go into additive, which is also good in some sense. But the transformation to go from technology readiness level 4 to 8 will not happen in that. It will go from 4 to 5 and it will get stopped there. Concurrently, if you know 8 and in a 5-year time frame, what does the business need to, let's say, put a fuel nozzle from this conventional to additive? Heat exchangers, for example. I think every turbo machinery or non-turbo machinery has a heat exchanger, but very few of them have actually gone into fruition. So you need to look at the right heat exchanger to replace. So it's not as difficult, I feel, simply because, and then people are talking about tools, cost. I see a few questions here also. The cost of additive has to be weighed against, let's say, you're spending, let's say, 50 lakhs in the development process in a 1-year time frame. In the 2nd year and the 3rd year onwards, are you going to give 2 crores to the business? I think that's a kind of an order of 50% greater order of magnitude, and it's not difficult to do by reasonable leaders, subsection managers with their teams. So that would be the strategy. Just low-hanging fruit, but at the same time, I would definitely urge those, whichever sector it is, to also look at near far 3-year time frame to do their own internal R&D as to where that is going to be to beat the competition. Remember, everybody is following the similar strategy. So they do have to invest in a little bit of R&D to see, it may succeed, it may not. So that would be my recipe actually for the technology readiness level, and to actually look at the fruits ROI really, really fast. And we can do it. It's just that you don't go in a mass mindset that I have to replace the part. I still find that in 2-3 year time frame. 2017 was okay, 18 was okay. Now in 2021, we really need to jumpstart and adopt it in more areas than one.
True. Very well said. I'm sure people will realize the importance of using the additive manufacturing technology in their manufacturing setups, and how they can overcome the current challenges of time to market, faster production, as well as the impact on the environment. I'm sure this technology will definitely get acceptance in the near future, even in the Indian market as compared to the Western markets. So I have a few questions, not few, there are many questions, but we'll take only few due to time constraint. I will just read out to them. What is the cost advantage in the aerospace domain compared to current manufacturing processes? Any one of you can answer.
Surendra, do you want to take it?
Yeah, I mean, I have 1 or 2 examples with the Indian space program and 1 or 2 with the missile. We have really not worked anything on the aircraft and aircraft engines yet. But I think there we saw a cost advantage of 1:3 very clearly in both the defense as well as in space. And that is with the limited numbers. I mean, I cannot imagine that when it comes to our examples to the aircraft, it will be far higher. As you know, that Indian space program is not really reached to its full maturity, where we have flights every month or every week or something like that. But with the limited number of usage, still it is showing a benefit of 1:3.
How to retain the mechanical properties X grain structure in traditional machine parts?
That's a real challenge, and that is where I also spoke in earlier, that obtaining a particular grain structure, you have to really play around with the 3D printing parameters. I mean, your heat input, which is there, has to be really manipulated. And maybe like in casting, we put some chillers. So similarly, during the printing, maybe some areas we need to chill it fast, or we may have to have a directional chilling, so that we can get the grains in a particular orientation. Second, I think the size of the powder also matters. Today, getting a powder less than 50 micron is not that easy. It's very expensive. But ideally, if we can get a powder of 10 to 15 micron, then it will become far easy to get a particular grain structure into our components.
Okay. And can 3D printing compete with the mass manufacturing methods adopted particularly in the automobile sector?
At least my personal feeling is, as on today, with the kind of machines we have, it will not.
Okay.
But I'm sure that it is going to have much beneficial. I mean, when I started 30 years back, my career as a machinist, I used to use machines with 3000 RPM. Today, the RPM on my spindle has gone to 60,000. And what the time I was taking with 3000 RPM and with the limited the torque on the spindle, with the practically infinite torque, which is available at 60,000 RPM on the spindles, the times have come down drastically. And similarly, I see that once the technology will start getting more and more accepted, the innovations in the machine building will also take place, and the machines will become far, far faster.
Okay. Yeah, the next question I think Dr. Deepa can answer. Is there a data that shows the achievable strength and quality of the part manufactured by AM? Is the part quality and strength going to be the same from first part to 100th part to 1000th part?
Sure, that's a very good question, but I just want to answer I'm seeing a few chat comments and related to the grain structure of the previous question. It's very, very alloy specific. In some cases, we have actually used it we have got much better strengths simply by using the advantage of rapid solidification and additive manufacturing. So it is very dependent on the temperature and the application, the loading conditions of the part. If it is just going to be a static part where you're flowing a water or a fluid, then the things to look out for are not really the strength, but is to look out for surface roughness, for example. So I'm seeing a lot of questions in the chat. For all of them who've asked technical questions, this is my recipe. Don't do, like a Tula comparison of this versus this, because this is a very different beast. It is completely rapid solidification. So not just in the immediate usage, we don't even know what is the long-term stability of these. By that, I don't mean to sound pessimistic about that it's not going to meet the cast part. I'm sounding optimistic by saying you need to understand it just like a doctor feels a pulse of a patient. Every patient, we all have specification of the pulse, but mine is different from yours, is different from somebody else's. So we have used it. We can tweak it to its advantage. To, for example, fine grain structure, directly solidified structure, grain structure, we can tweak it. At the same time, I'm saying it's not applicable for all temperature ranges. You have to look at the form, fit, and function of your application, even with the change design of DFAM. I'm sorry, I took a leaf of the other question, because a lot of times people think it's one versus the other. It is not at all like that. Sometimes it will be poorer than a cast, whatever you do. Sometimes it will be better than a forged with with a lot of luck. Sometimes it will be good for room temperature properties, which your service provider or your own 3D printing, that is not even the start, that is the 0th level. If you're looking for let's say a tool and die application, you have to look for that. section thickness, conformal cooling, and do the due diligence for that part, for that condition. So you can use it to your advantage, including high temperature properties. You may not. I'm not, so there's so many alloys. I'm sorry, the actual question you were asking, the 100th part, I think that's a great question. The only way to do it is if you're looking powder bed fusion process. I see Dr. Vishwas has just joined, so I'm going to talk specifically about powder bed fusion process. He's just built a huge machine, first of its kind in India. So where and what you do is just like you do for any qualification. Surendra mentioned earlier that in a rod form, we're going to be taking coupons in a forging from different pieces. Here, if your footprint is going to cover, your part is going to cover the entire footprint, find ingenious ways of making qualification samples. You can do that. I mean, you just have to use your innovation for that. Or if you're having multiple parts, let's say 100 blades in a footprint in the new ACE Micromatic machine, then you find a way to sacrifice in the corner versus the edge based on whether it's a recoater side or the other side. Qualification has to be done, whether it's a casting or a forging. And unfortunately or fortunately, you can build that qualification into your build plate, whether it's a direct energy deposition, electron beam melting, or powder bed fusion. The only thing is, and sometimes you have a very big part, you can have a gradation along the length and along the width and along the thickness. So sacrifice one part, check it up, and then use in situ methods to do it. So it can be done. I don't see, to be precise, I don't see it any difference as far as qualification goes from the 10th to the 100th to the thousands. You just have to do the due diligence with the right technical team and build it into the specifications. At the same time, let me also give you the con side. I'm not trying to simplify the whole thing to say everything is hunky-dory here. But we're all technical people. We all have good technical expertise, especially in India. We have legacy, knowledge. We just have to pull together, help each other, and do it.
Good, that's good. So I would like to stop here. Thanks to both Mr. Vaidya and Dr. Deepa for their very active participation and sharing their views. We really did good justice to the topic today, and it was a pleasure having both of you in the session today. It was really a fantastic session, I should say. Thanks for your inputs, and we look forward to have maybe another session, because I think I myself have many more questions to ask you, but because of the time constraint, we have to stop here. So thanks again. Thanks for joining us. Over to you, Dwayne.
For inviting us. Thank you.
Bye-bye.
Thank you, Mr. Vaidya. Thank you, Ms. Deepa. Thank you, Mr. Jitka. That was indeed a very engaging chat. Now, ladies and gentlemen, moving on. We now have a technology presentation by Mr. Sumit Bengri, Head Philips Additive India. So, Mr. Sumit, over to you.
I cannot start my video.
Alok, can you give the rights for the video, please?
Yeah.
Yes.
Thanks. I just shared my screen.
Yeah.
Yeah, hi, good afternoon. Good afternoon all. This is Subit here from Philips Additive. So today I would like to present how 3D printing is complementing the conventional manufacturing process. So basically, Philips is Philips is a pioneer in traditional manufacturing industry since many decades. So we started 3D printing separate division called Philips Additive, which to bring the 3D printing technology into the manufacturing process with a partnering to Markforged. So going forward, so here we have a very interesting topic to present today. So change is the only constant. Stereotypes about additive manufacturing, unlocking the manufacturing efficiency, real customers, real value right now. Then the Markforged platforms and process, and Philips machine tools solutions, and Q&A. So a lot changed. manufacturing is no longer simply about making the physical products. Changes in customer demand, the nature of products, the economics of production, and the economics of the supply chain have led to a fundamental shift in the companies do business. Nevertheless, but there are nothing lot hasn't changed, since there are process which has to be carried by conventional manufacturing, which cannot be replaced. But yes, the things are happening to change with advanced technology. So the Markforged machines have smarter, connected, accessible, and scalable, where the new age manufacturer needs modern equipments. So the modern equipments, what all to be required, are already adapted by Markforged machines. Poll questions, please, Jerry.
Can we please have the first poll on screen? Can we have the poll? Yes. So for what purpose are you using 3D printing is the question. Hobby, prototyping, concept modeling, batch production of end-used parts, tools and fixtures, or not use a 3D printer. So you have 10 seconds to vote. Please go ahead and vote. Yes. Can we have the results for the poll? Yes, so the maximum vote has gone to 46% not use a 3D printer. Then we have the second vote of 26% to prototyping concept modeling. Then we have 7% to batch production of end-use parts, and then the least is 4% for hobby. So that was the poll. So thank you for voting.
Yeah. So now we could see a lot of the percentage was more into not use 3D printer. So I'm here to showcase the upcoming slides, how it will be beneficial using 3D printed parts into a manufacturing industry. So how the industry so there is a revolutionary change in the traditional manufacturing process, where people are adapting into the 3D printing parts, considering the various options, like whereas the cost effectiveness, time saving, and many other points. Sorry, some technical glitch. One second. Yeah. Yes, 3D printing and the CNC manufacturing is a very unique combination. So where you can see the ice tip, the berg of ice tip, and at the bottom, at the sea level, there are a lot of inventions, a lot of efforts been implemented in the 3D printing to bring that 3D printing into the manufacturing industry. So when we say this graph, the 3D printing actually adopted in manufacturing by aerospace and defense in 2014. So followed by the tooling and fixture in 2017. It's only then followed by with a high and mixed low volume production in 2018. But now in 2019, the actual usage of 3D printing in manufacturing industry being started, replacing the traditional process. There are many parts which has been earlier there was no other options to go only with the metal, but now there are the possibilities where we can use the composite technology which have been adapted by the Markforged, which is bringing to the manufacturing process, where the actual even composite parts which give strength which can be replaced with in terms of metal. The jury, next poll questions, please.
Yes, can we have the second poll on screen, please? Yes. Do you believe that 3D printer alongside your CNC machine will add up value? Your options are yes, no, and not sure. So vote away. You have 10 seconds. Yes, can we have the result for the poll, please? So 68% have said yes, while 30% are not sure, while 2% say no. Thank you for voting.
Yes, so now and people are already adapting now, which we can see with the polling. People are adapting the 3D printing or additive manufacturing in CNC manufacturing industry, or you can say the traditional manufacturing processes. Just a second. Yeah. Sorry. When we say about there is a unique combination between 3D printing and the CNC manufacturing. So where we say unlocking the manufacturing efficiency, you can see in the screen, which defines a lot of parts being printed by using the 3D printing machines, like the fixtures, CMM fixtures, drone parts, landing gears of drone parts, punch and dies, and the lot of mechanical parts which using the composite as well as metal being already adapted in the industry segment now using the 3D printing. So going forward, we'll show you the much more examples how the 3D printing is complementing the traditional manufacturing process. So you just don't go my words. As I said, don't just take our words for it. It's a real customers, real value, and right now. Yeah, so here one of our customer lean machine using the 3D printed parts on a vise or a soft jaws. This is one of the unique example where this is the part you can see. This is the 3D printed part which are used in a regular vise. It's with a complex geometry which are involved. This is not just a proto. This is using into the actual manufacturing process, or it is used in the traditional manufacturing industry. So let's see. Let's take their words. What they say using this technology.
One of the big challenges we had with the bending cell was to basically design and integrate everything in a really timely fashion. We were able to actually do it in about 6 months, and that would not have been possible without the additive. We found Markforged by researching for the best printers out there for commercial and industrial quality printing.
One of the parts we make at Lean Machine is an aluminum wire clip like this. The tooling in general, what we used to use was big heavy steel tooling like this to put in our press brake. So one thing we found we could do with printing was actually print these tools instead. The big thing that we saw with Markforged was it took a big step from a hobby printer to something that you can actually make parts out of. And we saw a few sample parts, and then we kind of jumped in with it and haven't looked back. So the first step is that you load the blanks into the trays, which hold 200 parts each. After that, the robot picks the parts out of that tray using an array system and then takes it into the press brake to bend them one at a time. Because of the 3D printing, you have complete control over the profile of your bend. The onyx is actually very good for friction, and it doesn't leave any marring on the part at all. So we have a much nicer part with the printed tooling, and it's easier and cheaper to make the tool, so it's kind of a win-win.
With the continuous fiber, you make a printed part that not only could compete with aluminum parts, but in many cases actually be a better part. So one of the biggest real gains that we found with the 3D printer is that if we want to get parts made, we don't have to go and schedule them out in the machine shop. We don't have to order tools. We don't have to make drawings. We can skip all of that, and we can just get the parts made on the printer. We come in the next day, the parts are ready, we can start testing with them, and we don't have to go and check that they're right. And being able to have every single feature on a printed part coming out within 2 or 3 thou with Z accuracies of less than 1 thou. I mean, the accuracy stuff is huge.
As soon as we heard about metal printing, it's the next level, so we started looking into it. We're excited about it because, I mean, if we can make some tools work really well out of plastic, it kind of blows your mind what we could probably do out of steel.
For the grippers, they'll just look really awesome on there. The metal printed parts look nicer than most machine parts. We just keep bending thousands of parts, and the tools are not wearing. They're just bending perfect parts. It's like, okay, these guys can pretty much do anything.
So this is the custom voice been totally printed by 3D printing machines from Markforged. So you can see this is a non-marring the Onyx, where the and also the functional strength where with a reinforced with a carbon fiber to have a extra strength enough to handle the clamping and machining force. This is one of the unique, you can say, the example where the 3D printing is now involved or used, adapted in the conventional manufacturing industry. So this is one of the example where this again, the work holding, where the voice and soft jaws been 3D printed according to the complex shape of the part to avoid to making these parts in a normal conventional process. Going forward, we have custom end arm tooling. This is the Markforged has a USP in custom end arm toolings, where now you can see a lot of automation companies can adapt the 3D printing process with from the Markforged using the Onyx material with a reinforcement from the carbon fiber, where we can get an extra strength which can hold to the part, and also the time consumed is less, and any complex parts can be 3D printed using Markforged machines. So this is one of the unique example. This is the turbine blade, where it's a CMM fixture being printed by Markforged. The CMM fixture for this part, it's required extra strength. It's more complex. It cannot be made with a standard process. Of course, it can be, but it takes a lot of process involved, a lot of setups are involved, and a lot of manpower, time involved in a traditional process, where been printed on a Markforged machine, this CMM fixture. The main challenge was inspection fixture requires enormous time and cost to machine, because they must be highly accurate, repeatable, and strong. So this fixture with being printed can be machined on the conventional machines to get a higher tolerances. Yes, the solution, the Markforged 3D printer produces the complex geometry with any orientation required to the part for efficient, secure work holding of variable low volume parts. The final result, the customer can design and test fixtures within the same week. The lower material waste and exceptional quality and precision. So this customer has saved 70% of the time on the manufacturing process being saved once this part is printed. And one of the unique example which we come across day to day in our conventional or traditional manufacturing process, that is the tooling, the special toolings. As we explained before, the demands are increasing day by day. So the precision level is also increasing, and the complexity of the part is also increasing. Once the complexity of the part increases, you need to have the complex toolings as well to get the desired accuracy to the end application. So now the challenge is, when you say about the complex toolings, so what is the cost? So, and what time involved in it? So now the demand is changing very frequently. There is we cannot wait for a longer period of a time. So the solution is print the tool using Markforged. The tools with a special design, special complexity, or a special design or complexity can be printed on a Markforged machines, metal Markforged machines, where you just design a tool, print it, and the tool will be ready with a shorter period of time compared to the traditional manufacturing process. The cost is also pretty less. There is the involvement of manpower is also went almost zero down. And next, the number of machines involvement is also pretty less here. So you get the desired accuracy, you get the desired part in a shorter time with a lesser cost. Going forward, these are some of the images of the, these are the practical images where the Goering adapted the Markforged machines to implement the special tools using 3D printing. Yeah, this is one of the unique examples where the Siemens also adapted the technology, 3D printing technology in their manufacturing shop floor. On the it's a field on a field actually. The field service engineers required at a faster rate. So yes, the Markforged has a solution. We have a kit. It can be installed on the field itself. So they can design the part and print on the field. So let's hear from them.
Innovation Center, we're an end-to-end solution provider within Siemens. We're able to take a concept all the way to final implementation, all under one roof. So we saw the capabilities of the Markforged printers, and we saw the finished quality we get from the prints, the strength of the material, and we wanted to have a more industrial printer to be able to fast prototype and also potentially using it as a final tooling. When we first used the Markforged printers, a lot of people thought it would just be used for prototypes. And so there was an initial surprise by our end users that we were actually giving them a 3D printed part that they could actually use in the field or in a repair facility or manufacturing facility as the actual tool.
The major benefit of having the 3D printers in-house is that the time to develop an idea is dramatically shorter. Within a day or 2 days, we can go from an idea that we whiteboarded to a CAD model to a 3D printed part in our hands. So it drives the cycle time down as well.
The Markforged industrial printers act as a digital factory for us. In the past, you would have to make design decisions, do down selections during the design phase. We can now take 3 or 4 different designs, print them out, do the form function test, and then make a decision there which way to go forward. It just allows us to cut costs, and that money is realized back within the business units.
So with the Markforged 3D printer, we get great resolution on the parts. It looks like a real tool that you would buy from a store or something that would be in production.
So if there's an issue with one of the gas turbines out in the field and it has to go down, that means the lights go out or power has to come from somewhere else. So we developed this contoured cutback tool that allows the technicians to make a precise cut exactly where they need to. So this entire contoured cutback tool has been 3D printed. The only off-the-shelf components we had to use were some screws and the actual pneumatic spindle. We were printing this tool as a prototype, but we found that the Markforged carbon fiber composite material is actually robust enough to withstand field use. So we developed 4 kits that are deployed locally.
The Markforged printers have allowed our engineers to be more innovative by encouraging them to fail fast. It allows them to print multiple different designs, make changes to them without having to do that in a design space. And it allows them to get to a final solution quicker, to respond to these rapid prototypes that we have to develop for our business. With the additive manufacturing and the industrial Markforged printers that we're using, the sky's the limit.
So going forward, we have one more unique case study which is the Markforged. The machines are working at a defense in US. So you can see this part is pretty small and it looks very simple, but this is one of the main critical part. So one of the fighter aircraft F-35 was down due to their landing gear door assembly hinge was failure. So for them, it has to the only solution what they had before is to replace the entire door assembly. But with the Markforged machine, they printed this only the small part, the hinge, on the field itself, and been installed on the door assembly. So and the flight the plane get back to the air. So this is the uniqueness of the Markforged machines, where the parts now we can see are more accurate, more reliable, and can trust these parts, which can be used in all the various applications. Going forward, we have a high-end aerospace applications where the lightweight cabin components can be printed, the brackets, harness, and sensor mounts, precision inspection toolings, work holdings, functional prototypes, turbine hardwares using Inconel 625. So these parts can be printed on the 3D printing machines. So we say unlock manufacturing efficiency. Just I want to summarize what I showcased you. Just this is a summarize to give you some heads up on this, where as I said, the lower production cost. So in the manufacturing industry, when you implement a 3D printing process, you can lower the production cost. Next, free up the machinist talent. So we say use your CNC machines to make the parts rather making the fixture elements or supporting parts. Like you print the parts, you print the fixture and use the part on the machines for making the components. So improve the your output, increase your profits using the 3D printed in manufacturing process, shorter product development cycles, design and print, faster changeover. Now, as we see a lot of upgradation in the technology, a lot of improvement in the new technologies are coming up into the industry. So a faster changeover can be adapted. And of course, reduce inventory and overheads. So what instead of putting stocking the parts which are eat our profits, print whatever required today. Then tomorrow, today and tomorrow, what you require, you just print it instead of storing the parts the decades. Yeah. So retooling and optimize. So you can see the image defines most of the things here. We can see a lot of conventional setups being involved in the manufacturing process. So that can be dropped down to having one 3D printed machine, where we say this is what we say the complementing 3D printing into the conventional process. So most of the parts can be printed using the 3D printing machines. So earlier there was no choice, as I said before. Now we have a choice. Can be cut down the cost, can be cut down the multiple setups using the 3D printed Markforged machines. Yeah, going forward, see, there are three pillars of Markforged. One is strong material, then the cloud-based software, which is so intelligent. Just feed the model, it give you the process. Next, the robust machines. These are the three pillars of Markforged. This is the profile of the Markforged machines. We have a desktop series machines like Onyx Pro and Mark II. These are the can print continuous fibers, where can be replaced the aluminum parts using our base material called Onyx with a reinforcement of carbon fiber. Next, we have industrial versions. In the Onyx and the X3 and X7s are the composite printers, where this industrial versions having a little bit bigger build volumes. It can print again same with a carbon fiber reinforcement and other fiber materials, which can give extra strength and can be replaced according to the applications in the manufacturing process. And we also have a metal printer called Metal X, which is used in printing the tools, which can be it can be used to print even in copper, then the tooling parts. Going forward, as I said, this is one of the strong pillar, like the material is one of the strongest pillar of Markforged. So the Markforged come up with a wide variety of materials. The base material, what we have, the Onyx and the nylon. So we have a carbon like a fiber material which can be reinforced depending upon the application requirement. Like we have a carbon fiber, we have a Kevlar, we have fiberglass, and we have aerospace grade materials as well. Also the electronic industry which can withstand the higher temperature. Going forward, we also have in metal with a wide range of materials. Our metal machines can be printed with the 17-4PX stainless steel, Inconel, H13, D2 and A2 and copper. We have a wide range of or wide segments, I would say, where we are present. We present in aerospace, we present in automotive, we present in government and defense, we present in consumer products, we present in energy and heavy industry, electronic and materials, and medical and healthcare. These are the you can see the names where all these are the high prospect customers already using the Markforged machines and getting the advantage of it. Going forward, Philips, as I said, Philips is one of the pioneer in the traditional manufacturing industry. The Philips India, what we are here, it's 100% subsidiary of Philips Corporation USA. We have more than 10,000 installations of conventional machines. We have a technical centers all India, equal to 11 technical centers in India. We have 2 additive labs in India as well as in US. In India, we have in Pune as well as in Bangalore. We also cater to solutions, like we are solution provider, like we cater into turning, milling, grinding, EDM. So automation, we say tool to mold. So all the applications which are involved in the traditional manufacturing solutions or industry that been provided by Philips. And also we proud to say that we are one of the largest distributor of Haas machines globally. So talking to Philips Corporation, it's leading machine tool dealer worldwide over 57 years, having a presence in USA, Middle East, India, Sri Lanka, Bangladesh, and China. So these are the product portfolio what Philips give a solution on traditional or conventional manufacturing process. We have a milling, we have a turning, we have a grinding, we have a additive manufacturing, we have EDM and wire EDM, we have automation, and we have injection molding. So as we said, we are into mold to tool to mold. So we cover all the categories of conventional or traditional manufacturing process industry, which Philips can provide a solution to it. Yeah, before I end, I also would like to announce here we in Markforged desktop series Onyx Pro, the model, where we have come up with a promo along with our conventional machines or traditional machines, where we are offering a 35% discount on the Onyx Pro machines, so that these discounts are rolled out to enhance the market potentials. To each and every industry should adapt, manufacturing industry should adapt these machines to feel the revolutionary change. They should, once they adapt, they can understand the process involved, the strength of the machine, and this is the first step of additive manufacturing, which the small, medium, and large scale industries which are not into, they can opt for it and feel the difference. So we have a lot more information, lot more updates. So I request, please be with us, tuned with Markforged and Philips. So where we have a lot of things, a lot of offerings to you. Please stay tuned with us. Thank you.
Yeah, thank you, Mr. Sumit, for that very interesting presentation. Now, I would like to ask Mr. Jutkar to please take over and ask our audience questions to you.
Yeah.
Thanks, Sumit. It was a wonderful presentation. Lots of insights on the 3D printing and a lot of practical values. And the video also was very practical, showing all the applications of 3D printing. Currently, there are no questions in the Q&A box, but I would like to request all the attendees to put in their questions so that we'll get it answered from Sumit.
Absolutely.
Yeah.
Thank you, gentlemen. It's now time for the most awaited session of today's summit, the panel discussion on how 3D printing will impact traditional manufacturing and supply chain. So I would like to invite our panelists to join us. So Mr. Kripal Bedi, Head of Design, Sridevi Tool Engineers, Dr. Vishwas Putige, Business Head, Amaze Solutions, Mr. Ashok H. Verma, Stealth Startup 3D Metal Printing, eFesto 3DP, Mr. Raja Shekhar Uputuri, co-founder and CEO Think3D.in, and Ms. Swati Sumal, founder, The Art of Making Foundation and State President, 3D Printing Council. Do we have all our panelists?
Now it's unmuted, so yes, now we are here.
Yes, I think we have everyone now. Okay, so welcome panelists. So manufacturers from all industry sectors are exploring which items they may be able to produce using 3D printing technology. And the implication of 3D printing on the industrial manufacturing market is often heatedly debated. So some experts in the industry feel that it will be hugely disruptive, while others believe that the technology is decades away from viability. And at the same time, the industry is making rapid advancements, and it's only a matter of time before we see it significantly impacting global supply chains. Mr. Raja, I would like to come to you first. So the concept of digital inventory is a big talking point in terms of digital transformation that additive manufacturing brings. So could you explain the ultimate checklist for a good digital inventory strategy?
Okay. So good evening, all of you. It's nice to be part of this panel, and I've been following the sessions for the last 1 hour, and it's very informative sessions being provided by many people out there. So good strategy for digital inventory. I'll actually give a live case that we worked on. Maybe that can be basis for some of the answers for this particular question. This happened in, I think, in 2020. We worked with Navy for the impeller components. Navy guys came to us with one of the impeller components. The impeller is the one that sucks in the water and circulates the water from the seabed. Are you guys following me?
Yeah.
Okay, fine, great. So they came to us. They got this casted bronze impeller, and they don't have the designs for those impellers. And the ships are Russian-made 1960 ships, right? And the designs are not there. The people who manufactured those components are not there. So pretty helpless. And even if they have to do it manually, it takes around 6 months just to do the whole master pattern and then make the impeller is what they said. Maybe if not 6 months, at least it takes 3 months. And maybe what happens is that the entire, when you look at the manufacturing of a part, it is the pre-ordering process, that is the PO, and the post-ordering process. This all takes a lot of time for the organization as big as Navy. So they came to us, and then we showed them. Of course, they heard about 3D printing, and we are located in our facility is located in Vizag. They came to us, and we showed them the facility, and then we did an experiment. We did, of course, digitization, which is using 3D scanning and reverse engineering. We converted that physical part into a digital form, and then we used 3D printing using glass-filled nylon to manufacture that, and we did some simulations, right? So and it worked actually. I mean, we did some virtual simulations, but in the physical part also, though it didn't go for 3,000 hours, it went for 2,400 hours, 2,000 to 2,400 hours for the first part, and it's a good surprise for us also that it did work. So to address that question, no, this is actually digital inventory. If you look at it, right, this is the digital inventory, and then Navy was very excited about this. So they were like identifying the components. What all can be digitized and what can be 3D printed. Okay, so now with this as a background, with this as a live example, live problem statement that has happened, for which we could offer a solution by coincidence in a way, I can see some recommendations for a good digital inventory. So one is, not every component. One is having the digital inventory of all the CAD files. That is ultimate, very, very important one. And that's what we understood, right? But then not all the CAD files or all the designs will be 3D printed, right? Ultimately, it boils down to cost and time. Whatever you may say about disruption, this, right? Cost, time, and properties. These are 3 elements to. Of course, regulatory also comes into picture. But then if you leave the regulatory part aside, cost, time, and properties. Those are the 3 parameters on which you evaluate any manufacturing process or any material. So not all needs to be 3D printed, but then some of them, definitely it's cheaper to go for 3D printing. And also the context, how quick you need the part will also add to the decision making on whether you go for 3D printing and all on traditional manufacturing. First is you need to have a repository of all the components.
Okay.
Second is, you need to first identify, you first have to do a study, and that itself is one of the major activities that we do on which ones can be 3D printed, which ones are recommended to be 3D printed, which ones only by 3D printing you can do, right? Maybe through DFM and all these things, right? That is the second exercise. And third important thing is, which is something a lot of research is going on. Once you make it digital, it is very easy to do copyright infringement or patent infringement. You can easily transmit those, right? How do you secure those designs, right? That is another very, very important aspect, especially when you're looking at a digital inventory concept, right? How do you secure it? What kind of cyber security elements you need to incorporate into the whole workflow, right? And right from the manufacturer to the vendor, to subparties who are manufacturing. That is the third aspect of this entire digital inventory. Good strategy for digital inventories. So yeah, these are three things, and many people are working towards that. One is, cyber security element is one thing, but they're also working towards incorporating some nanomaterial into the designs, where the system can detect it and then figure out that this is an IP protected design, and then even sometimes they're working on one common open source framework where the printers won't print those kind of components unless there's some explicit approval given or things like that. That is another thing, but that is more of the industry standards that are coming up. But these three are the very important elements of a digital inventory setup. Yeah, I hope I addressed this question to a certain extent, if not to the complete extent.
Yeah. Yes. So that makes sense what you just told us, and that's very well put. And I would like to continue with you only, Mr. Raja. So now I'll come to the main problem that we are all dealing with today, that is the COVID-19 pandemic. And it is no exaggeration that the COVID-19 pandemic has changed life as we know it. But how can we build a more resilient supply chain in the future through 3D printing, through this COVID-19 pandemic?
Sure. So yes, there are a lot of articles on the media about how 3D printing is used to make face shields and all these things, right? So it's good, 3D printing for face shields, right? When you need it on demand, right? When the entire transportation systems were locked down or were broken down, it's good. But if you look at the cost analysis, which this is an exceptional scenario. Lockdowns is a very, very exceptional scenario, once in a century scenario that has happened, right? So that can't be the basis for decision making for resilient supply chains. I don't advise or advocate this to be the fundamental basis for building some resilient supply chains, right? So very expensive to do it. It's not how 3D printing should be implemented. It's not for like face shields or those very basic elements, because that's the area where it doesn't have complete advantage also, from what we've been hearing all through. But what is happening is the systems, the global supply chains have become too efficient, right? Extreme efficiency is not always good. It has become, all these principles of JIT, just in time, vendors on demand when they call the material to come, right? So it has become too efficient that has become an Achilles heel for this during this lockdown, right? There were no inventories everywhere. Now look at the car production. Vietnam and Malaysia, there was a lockdown, and Toyota in Japan had to stop its production, right? So this is not how it should be. Right. I'm addressing a different topic here. It's about, resilient supply chains need some inventories. Inventories may lead to some cost, but at times it helps, because JIT is an extremely perfect, well-oiled engine, which is not always the case, right? And when such disruptions happen, and because of natural calamities, disruptions happening, climate change, lot of disasters are happening, which may lead to lockdowns in different areas. Right, that is where I think 3D printing can play a role, right? So, meaning whenever there is this gap, which we call as batch production or short gap, in a way, short gap production is what we call it as well, right? Whenever there is such a gap in replenishing the stock, we can use 3D printing to manufacture for that particular time period, where there is a shortage in the unit, right? And once the material is replenished, then they can go for the normal, whatever mass manufactured components on the material, right? So currently at this moment, 3D printing can be used for shorter production because the cost of manufacturing using 3D printing for a given design, and for most of the designs, I would say, is still higher than for traditional manufacturing, right? So maybe for unique designs, complex designs, deformed designs, yes, it is cheaper with 3D printing. But when we say that, that may be considered around 10% of the overall designs or overall models out there. But 90% is still expensive to go for 3D printing. So it can be used for batch production or shorter production until the material or inventory gets replenished.
But do you think this will make a more resilient supply chain for us? Do you think this will lead to a more
Exactly, this will definitely. I mean, 3D printing is a beautiful on-demand, local, on-premise manufacturing technology. No other technology has such been, right? And even if normal CNC or forging or foundry and all that, you don't have it in your office setup, right? These are some, even within the country or within the city also, one would be some other location, remote industrial area, whereas the plant may be in some other location. The beauty about 3D printing is, the way it is, the whole system is designed and all that, you can have it in your factory, you can have it in your office space as well, right? Very near to where maybe the assembly is working, and very near to where the production is happening for any kind of product, And then it can create a very resilient on-demand. It can shorten the time it takes for manufacturing the goods, or for time it takes to what we call to assemble the whole part, right? So that way, yes, it helps in resilient supply chains for sure. I'm just saying that cost is also a factor that we need to consider whenever you're talking about disruptive technologies. Yeah.
Right. Okay. Now, Mr. Bedi, I would like to come to you. How will 3D printing impact the traditional manufacturing and the supply chain?
Hello, everyone. Since I come from the plastic mold making industry, and I would like to be, I will be more accurate if I speak from the user perspective and from the plastic mold making industry perspective. 3D printing impacting traditional manufacturing. Like if I look back and see, just come out of the situation and see how it has impacted us, is that we are getting much more better product designs to us for mold making or for tooling. Because all the testing, virtual assembly or physical assembly, prototyping has been done in the design stage. And people are now able to touch, feel, assemble the parts, and they are really confident of their designs, and then it has been given for tooling. So this is the indirect way in which 3D printing has affected us in the traditional manufacturing. A good product design means we can finish the molds quickly and they can get into productions much faster. In the previous days, the designing used to start after the first trial parts were submitted. They would assemble the parts, find some cranky issues, and again the tool used to go for modification. This is not the case now. You can all find us completing molds in T0, T1 and finish. There is not much ECN going on. It is because 3D printing has helped us. Second way in which 3D printing has impacted us is that we can now produce critical mold inserts with the help of 3D printing. Previously, we were not having the advantage of conformal cooling. Now we can do conformal cooling on our molds, and this can help reduce cycle times and give better quality products. Now, what does that mean for the traditional manufacturing is that you get more machine molding time available with you. Your much more conventional cooling, whereas you have a 40-second cycle time with the conformal cooled part. So you can get more production out of your molding machine. So this frees up the machine time. If you have a bad cooled part, you need conventional cooling fixtures and all the assembly line up, because you have to cool the part properly in the cooling fixture and then give it for assembly. Now that is not the case. You will never find cooling fixtures part of the norm of the molding machine. So this is how it has speeded up the process. Another area where we are still at a nascent stage is that hybrid printing, as in we can say that, wherein you print a layer, you machine it, print the second layer, you machine it, so that by the end of your printing, you are getting an almost ready to use insert. So this avoids your EDM, your electrode making, and all the cycle and all the supply chain which is going into all these things.
Mr. Bailey, I think we lost you.
Really remove so many things in the supply chain for us. Also, one area which is also very nascent and at this stage it is too early to say is that you are printing with multiple multiple lasers, producing injection molded quality parts at cycle times compared to an injection mold. If that happens, then the mold making itself will wipe out. Probably it's too early right now, but these are the ways in which 3D printing is impacting us, and we should be ready to and also be ready to adapt to it. That's from my side on this. Thank you.
Okay. So, Mr. Verma, now Mr. Bedi gave us the mold making perspective of this. So I have the same question for you, that how is 3D printing impacting traditional manufacturing and the supply chain? I have the same question for you.
Okay, I'll keep it very straightforward because I've done this for 21 years. So I have the things. Fundamentally, additive manufacturing / 3D printing, the number one benefit with this technology is reducing lead time. Number one benefit. It has all kinds of other benefits of design and making things you cannot make, but the lead time reduction is number one benefit. So, supply chain. In supply chain, the number one benefit for supply chain that I have learned from about 30 companies interactions now is reduction in inventory, because everything has to result in a profit. You don't do anything in technology if it does not make you money. There was no point in doing it. You're wasting your time. So inventory reduction is the number one cash benefit. You reduce inventory, you create the company cash. The second one, of course, is building on demand, because then you are reducing your tooling costs and your manufacturing costs and your costs of factories. You build only how many parts you want to build. That's all you have to do. Correct. And Amazon and there's about 20 to 30 companies that have made investments in startups in US and Europe only to do build in demand. That's all. That is called digital warehousing, which Kripal was talking about. And the third thing that is simultaneous with that is building a location, distributed manufacturing. You want a part in Ahmedabad, you build it near Ahmedabad. You don't build it in Bangalore, or you don't build it in Europe or in Russia or in China. You build it nearby, okay? Doesn't have to be in the same city today. In 10 years, it will be next door, but that is 10 years from now. I'll be long dead by then, okay? The other thing about supply chain mitigation is you reduce the obsolescence of spare parts. The spare parts 3D printing, even though it is a smaller industry today, and there are only a few startups in this, and I'm advising 2 of them right now out of India, because India mein koi nahi kar raha ye, is there are so many components that the spare parts will take 1 month, 2 months, 3 months, 4 months, 5 months, or never. The defense, I'm working with ISRO and HAL and DRDO. A lot of the parts are from Russia. The materials are not even known. They're unknown. And I'll give you a random number because I cannot give you the exact number due to secrecy laws. In India, in HAL, I'm giving you an approximate number, okay? There's about, I just say in dollars, about $20 billion of spare parts over the 2 or 3 decades of adoption from the MIGs that are lying around in the inventories and in the warehouses that don't have a replacement, okay? I'm just giving you a simple number. So if you can build even 1% or 2% of the spare parts, that's a huge business, okay? Now, for supply chain reduction, from the environmental side, reducing the carbon footprint. So shipping by water or by ocean is about 70% of all transportation of components in the world, of parts, cars, everything, 70%. If you can reduce this by even start beginning 5% reduction, that is a multi-billion-dollar benefit. And the carbon footprint, because the ships are the #1 carbon footprint producer, and that is going to be very, very important for the world as you go ahead. Okay, that's not a business; it's a good thing to do. Now, talking about Army, and I'm working with some projects with the Indian Army, US Army, and Israeli Army, where when they deploy in the field, whether it's for practice or games or actual combat, if you have 20 trucks with the equipment and people, soldiers in it, you have another 20 trucks, maybe more, carrying spare parts for them, replacement parts. If you can print on demand, and Australia is already doing that with 2 companies. Right now, Australian Army has proven this. I have the articles, I know the companies. Print on demand, when you have a breakdown in a weapon system or in an armor system, print it right then and there in the field. Now, forget about the money aspect of it, that saves lives. That's what I'm trying to sell to DRDO. Save some lives of our Jawans also, okay? Then the obvious stuff. If you can print in-house, in country, on location, you insulate yourself from the random embargoes. I mean, America, I'm an American citizen, so I'm not saying anything out of line. I'm a citizen for 37 years. You protect yourself from the embargoes that a government can put on you, that we have sold you this equipment, but we will not replace it. We will not give you spare parts. We won't do anything for you. That is an amazing insulation for the defense and military. Okay, so that is, in essence, my view on supply chain advantages with additive manufacturing. That's it.
Okay, I see. That's quite a different take on what you said. Now, Dr. Vishwas, I would like to come to you. Now, post-processing, that is something we don't talk about enough in 3D printing. So what are some of the current challenges that companies face when it comes to post-processing, specifically in 3D printing?
Yeah, hi. Thank you, all of you. Yeah, and Julie, it's a very interesting question. See, actually, like you rightly said, post-processing is something which is hardly spoken about in the whole science or the whole process of 3D printing. It's something that people normally miss out on and paying enough attention to it. What people have assumed, of course, we have had some wonderful speakers who've given the good sides of additive, who explain all the strengths of additive and beautifully demonstrated some of the examples of additive. In general, I would like to say, not specific to any technology, but post-processing is something that is mostly ignored, mainly because people assume that it is something that can be done as a form of a jugaad or some small correction or a modification, and then we may have our end part, and that is where it normally ends up being unviable eventually. So people, especially at the design phase, end up forgetting how much effort is required and what exactly is required to finish parts to the actual requirement of the end customer. So doing that, what ends up happening, there's a small gap between the design and the production team, if there is a compartment of that sorts. So we normally recommend, what we've always seen is, out of our own experience, it is very necessary, very much necessary for a design team to look all the way through to find out what are the aspects that are involved in the whole process or the chain of manufacturing, evaluate each of those thoroughly with the discussion, and for probable deformations or rejections, or accounting for some of the criticalities. Each material is different. Each material has its own properties in terms of how it would behave in printing, how it would behave post printing, when you either heat treat it or when you machine it. Each material has its own properties. So what comes out of experience is to be able to judge and identify each of these properties and behavior of materials, and to accommodate changes in design accordingly, so that at the end of it, with minimum iterations, you're able to get a fully ready part at the end of it. So this is the prime focus. See, we've had our share of learnings. I wouldn't want to say use the word failure. We've had our share of learnings where we've seen, especially when there are micron level tolerances that are specified by end customers in terms of the end part. We've had to print multiple additional parts, which will help the machinist or a guy who would do post-processing to, as a sacrificial part, to be able to identify work holding, identifying cutting tool, to be able to decide the stock, to be able to do, to finally achieve that end part. So, but with experience, you get better at it, and then that's the small price one has to pay in terms of learning. And eventually you get to a stage with enough effort put in, where you're able to identify rightly for each material what sort of stock to build in, where, in what orientation are you able to get the right kind of dimensions, and you're able to judge, or it's a good marriage between the design, the machine, the post-processing, the behavior, the process itself, and the powders, or if it's a powder-based technique, to identify and then get to a stage where you're able to get right estimation or prediction of what you're able to do at the end of it. So it's necessary for the design to look at it in totality, which even normally gets missed out. People believe that just by taking a 3D model, which is there originally, pushing it into a software and then press the print button, you probably would get your end part, which is what is the small gap there, which would probably people have paid hefty fines for having assumed that. So people do realize that after doing that, and in many cases, people do realize that 3D printing is not a viable solution, which is not. I mean, it is how we make it work. How do we find a way around it? How do we work a way around it? We've had some wonderful examples that people have shared. Even Mr. Bedi explained a few things about hybrid. People have realized what you can do, how you can do, and make it work. That's a real challenge. It's people gave good examples, and they've told that this is a fantastic technology. It is something that could do miracles. But you need to tame the lion here and make it work for you, and make sure you get the right results. Now, coming to specific challenges, as I explained, machining, of course, is something that is the big giant there, which especially when you have tolerances close to what you would want on a conventionally made part and finish it to the tight tolerances that are there. So when you get to that, you do have to understand the concerns of machinists and what sort of dimensions and tolerances are achievable, and what you have to do in terms of correction to allow certain things to be achieved as a post-processing. And of course, something that people do end up missing out is supports. So as we all know, especially in 3D printing of complex geometries, we do have a lot of supports that get generated in parts. We do assume by designing a part by itself and then taking it for printing, and of course supporting it in areas that it would need, which is anyway necessary. We might end up getting the part out the way that we would want, but we've realized in many cases, removing those supports is a challenge, even to achieve open tolerances. To be able to get to a stage where these supports can be removed is again something which is quite difficult. So what we do recommend or do work on is to see how, in many cases, we have gone about giving suggestions for design change with our customers, where they're able to do some modifications to the input design itself. where we could minimize the requirements of supports itself, and also look at what orientation. And of course, invariably, what is necessary is the design has to have thorough discussion with customers to find out the actual application, the requirement, the critical aspects of the part which will have to be kept in mind before we take it up for printing, not discuss it as a post process or during the finishing of it, because you may end up wrongly identifying orientations or areas where you can afford to have supports or have reduced surface finish, if at all. So that's that. Taking me to the next point, which is surface finish. So external surface finish is something that maybe through either hand polishings or machining or other post finishing activities you're able to achieve. But a challenge that is still remain largely unanswered is improvement of surface finish on internal surfaces, especially as Mr. Bedi rightly identified. You have conformal cooling, which is doing significant change to the insert and die industry, which would bring out a lot of reduction in cycle time and hence improvement in productivity. But one of the challenges still remain in terms of is how do we clean that internal channel? How do we make sure over a prolonged period of time, what are people doing to make sure you keep it clean and remove the scaling that happens or the salt accumulation that happens, which is something that people have experienced and have been working on. There have been solutions. There are some new techniques and technologies which have come, which people are exploring and trying out. But that's still either at a very primitive stage of adaptation, or they're painfully expensive compared to the advantage that it might offer in a wholesome. So surface finish, especially from hidden surfaces, is something that is of a challenge. And as I explained, dimensions, achieving the right dimensions is something that people will have to work on and to get it right. And finally, I feel there's the requirement in terms of your properties, achieving the right properties to as a part of the post-processing is something that still is a question we get asked a lot by customers, especially because we have a strong feeling to compare the printed part with conventional part. I heard Dr. Deepa beautifully explain that please don't do a weighing or a comparison of a like-to-like part. You'll never be able to satisfy or achieve what you'd want. What would be right is to identify how 3D printing, to what extent 3D printing can match your actual requirement. I mean, we would all want to live in an ideal, perfect world, but it may not be right. We need to look at a mindset change here. People do think that they would want it to be perfect, but people don't realize a lot of innovations have come out of imperfections. We've had people who've today, in fact, one of the interesting topics that has been asked by the mold industry is, can we have porosity? We would want to build in porosity. We would like to have inbuilt porosities for various reasons. I mean, porosity used to be a big bane at one point in time. Now people are exploring, can we have lattice structures inside dies? Can we have it made with lattices and made it lightweight? So there are people who are converting these imperfections in either properties or densities. That we've worked with customers, of course, I can't take names, but people who say, hey, I'm fine with 97% density of your part. I don't care for a 99.9%. My application, 97 is good enough. Give me something which is much faster. So by reducing, we've had examples where we've gone about bringing down manufacturing or the printing time from, say, 10 or 11 hours to about 3.5 hours, only because a customer was willing to compromise marginally on the end property that they're able to accept. And that was sufficient for their requirement. Though people say, hey, look, as opposed to what you do conventionally, 3D printing may or may not give you the result. Like Dr. Deepa rightly said, let's stop drawing parallels to what is probably possible conventionally, but look at what is actually required for the application. How good enough is it? And by doing this, imagine by halving or bringing it down by about 60–70%, there are a lot of applications where it could swing towards being a 3D printable part rather than being deemed as a very expensive, unaffordable, and unprintable kind of application. So my point is that again happens at a design stage, not design just at an additive manufacturing stage, but the conceptualizing itself and then telling this probably is good enough. If it's a proto application, maybe for a fit form function of a small batch, maybe sufficient, and things like that. So I think post-processing also, from that perspective, needs to be looked at from a totality, and needs a bit of a mindset change, and looked at a very initial stage, and should be discussed at great length with the end customer's requirement.
That makes sense. That makes complete sense, and that's very in-depth to what you just told us. Now I would like to move to the skills aspect of additive manufacturing. So I would like to come to you, Ms. Swati. So Ms. Swati, you have an expertise in building training, teaching curriculum for industry-specific needs in additive manufacturing. So what I would like to ask you is that, is there a skill gap within additive manufacturing? And if there is, then what? Can you hear me?
Yeah, now I can hear you.
Okay, let me repeat my question. You can hear me now?
Yeah.
Yeah.
Yes, perfect.
Yes. So what I was coming to is that you have an expertise in building training, teaching curriculum for industry-specific needs of additive manufacturing. So my question for you is this, that is there a skill gap within additive manufacturing? And if there is, then what is being done to address it?
First of all, let me take this opportunity to introduce the Art of Making Foundation, what we are doing. So when you talk about this skill gap, it is again, it has different aspects to it. As we have been discussing today, that there is a lack of ecosystem in the additive manufacturing landscape. At the same time, there is a skill gap, and at the same time, there are printers, and the cost of materials are very high. So even if I train, or I have a huge pool of skilled laborers, where would they go? If we don't have an ecosystem, or they don't have an industry to go to work for, right? So adaptation of additive manufacturing is one of the things which we are really working forward to. And when it comes to the skill development part, or building labor force in additive manufacturing, we are currently working with around 80% of the women beneficiaries in our organization who are learning the basics of 3D printing. So we are targeting tier 2 cities where students from colleges. So again, there are 3 verticals to it. One category, which is school and colleges. The second one is working professionals who are already working in the AM industry, and they want to upskill their current set of skills which they have. And the third one, which we are currently focusing on, is bridging the gender gap in additive manufacturing by giving more opportunities to the women designers, the women entrepreneurs. So having said that, the whole ecosystem works hand in hand. We are developing the skills at the same time with the kind of ecosystem which we have in our organization. We have ties with the all tech startups in India and US as well. So they are doing and developing a product line for those industries. I'll give you a simple example. One of the girls in Uttarakhand, she is doing mandala art, which is ancient art, and she is printing jewelries of it via 3D printing. And those jewelries are being sold in the US market. Right now, we have not tested in Indian market. First, we are exploring the US market. So see, the skill, developing a skill is one thing. At the same time, giving them the opportunities, I would say that matters most to us. And that's why we are making an equilibrium, where at the same time, we are developing curriculums for toy making industries, for architectural plannings, for jewelry designing, for kitchenwares, and there are a lot of courses floating on e-learning platforms. That's how we are growing, and we are trying to bridge the gap which is there. And we are mostly industry specific, I would say. Jewelry making is obviously growing a lot in other markets and in India market as well. So we are focusing more, and we are kind of detailed oriented in terms of using 3D printing where it's required exactly. We know that there is a gap, there is a need. We do a market study that, okay, these jewelries are going to sell in a particular area. As someone mentioned that Koreans are very big in jewelry market. And so that's how we are going to explore it. So we believe in curating the industry specific curriculum, Julie. So with that, I would like to say this is how we are trying to build up and build curriculum, around it, around AM industry, I would say.
So are other institutions or other platforms are also making this effort to reduce the skill gap for AM besides your platform?
Absolutely, there are. So we have a global picture as well, where, in India, we don't have tinkering. We do have limited tinkering labs, I would say, where students get a hands-on learning experience, everything. So few of the curriculums are being developed at hobbyist level, not at the professional level. Few of the colleges in India, like COEP Pune, is providing post-graduation degree in additive manufacturing, while the rest of it, like NITs and IIT Kanpur, are providing short-term courses. So there is a gap where it needs to be standard, like the curriculum standard should be there, which should be in all the universities, just like a mechanical engineering is, just like electronics is. So that kind of adaptability amongst the education universities and colleges, we are kind of finding it difficult. We were finding it difficult 3-4 years back, but now there is a huge acceptance coming, because now the academics people are seeing the industries, they are adapting to it, and there is a requirement in the industry now coming up. So in coming 2 years, I have seen that literally there are job posts which are coming. They need dedicated CAD jewelry designers. These kind of jobs, if they keep on coming up in the market, then there will be a huge demand, and people will start learning those skills. So I believe there should be a demand of these skills first. At the same time, when people see there is a demand, they take this track of learning, and depending on the application, which is like very diverse for 3D printing, be it aerospace, automobile, healthcare, you name it. So based on that, people can have a channel that healthcare is what I want to do. Let me take this route of additive manufacturing study. So there is still, as you can see, these courses are missing as of now in India.
Okay, so that's a very interesting angle you put about the courses that are being made available. Yes, Mr. Verma, would you like to add something?
No, nothing.
Yeah. So I would like to now come to you, Mr. Bedi.
Yeah.
You have had many opportunities to work in global locations for various projects.
Right.
So what are your thoughts on the additive manufacturing operations and thinking additive scenario globally as compared to India? And what can we learn from those markets globally?
That's a great question there. See, we have been always a follower kind of a country, where we always look towards the West, and we are catching up faster because of the digitization, and everyone is knowing what everyone is doing. But as we see there, and as I work with these people, is that there's a lot of R&D going on in the West when it comes to 3D printing in terms of topology optimization, and a lot of software is being created for these kind of things, where as Autodesk Fusion also we have seen in that you just pick the points, place the load, and then they will create and generate the profile for you. When it comes to mold making, we have seen that a lot of people are working on auto creation of cooling lines, wherein, see, now traditionally, if you have to have a conformal cooling, you will go to your design, and human mind always thinks in straight lines and curves. He will always design a cooling line which he thinks is most suitable for printing. But when you give it to a software, they will take heat which is there in molding, which is the most area, which place has most heat, will have more aggressive cooling. And the cooling line can be designed more suitable to the process automatically by the software. So this is the kind of research which is going on there, and people can design the self-cooling designs. No need for a human to design a cooling line, the software will do it for you. So these are the kind of thought processes which we see are there, and especially in Europe, Japan also, many companies have done this thing. So this is where we need to keep looking at. And these are trends. But otherwise, if you see in terms of manufacturing or every company having a 3D printing machine, no. They still have the same kind of pattern where a cluster goes to a service provider, get their parts printed and bring it home. Not every company is able to afford a 3D printing machine. I have friends in US and Canada, they also go to a service provider, get their parts printed and bring it home. So having our own machine in-house is still a distant dream for them also. In China also, it's the same thing. Not all tool rooms have a 3D printing machine in-house. So the cost is still high and everyone goes to a service provider. So this and the service provider base is increasing. As in India also, many service providers have now come up and everybody is providing good services and everybody is eager to learn and give you the best services and best knowledge. And this is how we are increasing. And I find that the talent available and the intelligence in the Indian market is also good, and people are able to give you good suggestions for your designs. So this is the feedback from myself. Thank you.
Okay. So the talent is good, but then what is it that we can learn from global markets?
They are, they have now already optimized the way in which they are using printing. They are exploring newer and newer ways, and every day you will find that newer materials, newer ways of printing. You never thought of gold being printed, but gold was also vacuumized last week I saw, and then they have now a powder of gold. So jewelry printing can be done in real gold instead of printing on a metal. The gold is now ready for printing. We didn't have copper printing till a few months back, but now good copper alloy also can be printed. So these are the So these are the things that we need to keep an eye on and also adapt it quickly. We didn't have mold specific materials which are available earlier. We always had maraging steels which could be printed, but now we have mold related materials also which are ready in the market and available, and it can be printed. So these are the trends that we need to keep catching on and learn from the West in these terms.
Okay. Now, Mr. Verma, I would like to come to you. You work on the potential of AM for aerospace and defense. So how do you see the current state of additive manufacturing within these industries, and what are the key challenges that we seem to be facing?
In India or worldwide?
In India.
Okay. So yes, I would say over the last 20 years, I've been in metal additive manufacturing. I started with metal AM when it started. So I've been there forever. Defense and aerospace has been the focus. Now, what's happening is aerospace has a lot of certification if it is commercial aviation, okay? And that is a challenge and a barrier. Personally, if you ask me, I don't believe in that. But FAA and all these people are worried about crashing. I mean, that's their problem. But that is a barrier. But in defense aerospace, there are no barriers. The pilot will eject, okay? And I'm being very callous this way, but that is the reality that I have found working with Lockheed Martin and Rafael and HAL even, that we don't worry too much about the certification for defense parts compared to commercial parts. So my focus has been defense, even in aerospace, because commercial Airbus and Boeing and all, it's a waste of time. I mean, I'm an older guy, so I don't want to waste my time on that. So the challenges in defense aviation, I will talk about space in a second, are simply adoption. That's all it is.
Okay.
It's only about adoption. And I'm going to talk about US and Europe because I have 36 years experience there. India with HAL, with Tejas and all, that was a waste of time. So India aviation, even in defense, is a waste of time. For anybody who's trying to do it, it's a waste of time. Those people are fools. Until a private industry comes into India, you're wasting your time with the PSU for aviation in India. It's a waste of time. So in foreign countries, my home country, I'm a US citizen, they're looking more at propulsion and armaments. They're not looking at wing spars and engine mounting and all. They're looking at engine casings and blades and thrust nozzles and all of that, which is the right thing to look at, because a lot of the parts in a Air Force jet is made in aluminum, which for 3D printing is actually a waste of time, because it is much faster and cheaper to machine aluminum than it is to print it. But you're doing Inconel and titanium and some other new exotic alloys, couple of them I cannot name due to secrecy laws, I cannot name them. Those are where the printing will be. And that is what's happening. So my number one believer in 3D printing for defense aerospace is GTRE in India. Okay. And GTRE is the number one engine manufacturer in India. So they are smart people, not like HAL. GTRE has smart people. Okay. I'm just being very blunt about it because I can. Now in space, 3D printing will actually gain maximum traction. And I say maximum in metal 3D printing. I don't believe in plastic and polymer. It's a waste of time again. Metal 3D printing will be in space technology. The space technology industry within 10 to 15 years will be $3 trillion, 3,000 billion, which is bigger than the aerospace industry. Because the world has moved on and they're looking to printing rockets and satellites and propulsion systems and thrust systems and grid fins and all of that, and then structures on moon and eventually Mars. Out of my lifetime, moon, maybe I'm alive, with 3D printing. It's with some regolith, which is the moon dust and Mars materials, which let us see what happens, but mainly in titanium. Every printing that will be done on the moon will be titanium. Most printing that will be done in space by robotic measures for space station and all will be titanium and maybe some stainless steel. Those are two metals that we will do. And that will be the number one application of 3D printing in space. Now, if I talk at defense for non-conventional 3D printing applications, two things you have to do. Whoever the audience is, they have reduced from 103 to 64, that's okay. Go to the websites for United States Department of Defense and hit the location for Department of Defense Strategy for Additive Manufacturing. That was published only in January this year. It took 3 years to come out. I have some sections in that. The US Department of Defense has clarified how they want to use additive manufacturing for the US Department of Defense. Now, when they have done that, there is no country, no nation that can defend that. They can say, we have to do the same. A different scale, of course, because the US Department of Defense budget is equal to the budgets of all the countries in the world multiplied by 3. So they know what they're doing. US defense budget, and I know DRDO very well. I know Dr. Reddy. I know Rajnath Singh. Manohar Parrikar was a close friend of mine. He died, unfortunately. They have no clue what they're doing in 3D printing. They're messing around, million here, 500,000 there. US Department of Defense knows what they're doing, okay? So read that article, whoever wants to do it, 23 pages, you will know what defense additive manufacturing is all about. But eventually, the number one application for India will be in repair and maintenance of obsoleted parts you bought from Russia and God knows where, for re-putting in service. HAL itself has more than $10 billion of parts lying around in its warehouses that they don't know what to do. If you can touch 10% of that, it's $1 billion of repair opportunities. Indian 3D printing industry today, the entire 3D printing industry in India, entire plastic, metal, machines and services is less than $50 million. That is not even the top 20 of even the larger service bureaus for 3D printing in US or Europe. So India is way far behind. You have to look at the right applications. The business cases are obvious. I agree with Deepa, if Deepa is still there. business case is key. But if you're repairing defense components for Indian aerospace, army, and navy with 3D printing, the business case is obvious. You have no other replacement instead of ordering a new one from the original supplier, which will cost you 10, 20 times what it costs to repair. So that maintenance, repair, and overhaul is the major thing. Finally, I'll cut it short. I don't want to talk long. The potential for 3D printing in defense supply chain. So I'm combining the first question you asked with the second one, to save lives and to win battlefronts is absolutely incredible. So again, if people want to research this, go to the Australian Army site, US Army site, and the Russian Army sites, websites. They are looking and already proving printing of parts for spare parts. And as medical printing is getting more and more, printing some replacements of human parts in the battlefield for injured people. And those are the applications. At the end of the day, 10, 15 years from now, that is where the business will be. It won't be in building machines. It is all about applications. The whole thing is about applications. CNC machines 50, 60 years ago cost 20 times what they cost now. When I say Vishwas's photo on this, Vishwas knows that. A full-blown horizontal machining center 50 years ago was $1 million or $500,000. Now it's $25,000, $30,000. Same thing will happen in 3D printing, but it's all about utilization and applications, people using it. So it's all about business case for people making parts and an affordable machine. And that's all I have to say. Nothing more.
I see. Okay. Now, Dr. Vishwas, I would like to come to you. Do you think that designers take advantage of the freedom of 3D printing in the way they should? Like, do they use the complete abilities of 3D printing? And how should one think additive? Like, I even asked Mr. Bedi this question that about thinking additive, you know. So how should one think additive, and do designers take complete advantage of the freedom of 3D printing?
Beautiful question, Julie. I think we are not even touching the tip of the iceberg of what additive has to offer for us here, people. I think the single word that I have to answer is to think additive. Our designers have to first unthink the convention. They have to unlearn what they've been taught in design school and what they've followed for decades together in terms of how part printing, part manufacturing has to be done and what aspect of it should be focused on. So that is something that is slowing them down in adapting to the real strengths of, or rather leveraging the real strengths of additive. So my take to it is, there's see, we've always known and called designers as the apex body of any manufacturing. So they're the ones who can foresee the farthest. They sit at the top of the whole manufacturing pyramid, and they're the ones who see it through the life cycle, which is not just manufacturing or if there's an assembly, but even servicing and maybe eventually the end of life cycle. So they're the ones who should take that effort to see how that can be done. And my strong feeling is additive is actually a designer's paradise. If one can leverage on it, they can bring so many things to reality. Today, whatever technology we use in terms of designing or even simulating or analyzing, there's only limited information that you're able to harness from these technology. Ideally, you would be better off seeing it physically, using it physically, putting it to test in a very short time, and then taking a decision as to what is the right process, which is why prototyping was still is the most loved application of 3D printing and the one that's mostly used today, even today globally. Of course, now we've moved much ahead of rapid prototyping, but as they say, a good design is half the job done. So if someone can design right and design for 3D printing, which is what is the biggest subject I'd like to, stress on design for additive manufacturing is something that all of them should take up and invest in. I'd say if anyone who's interested, I keep telling this to people whomever I meet. If someone says, hey, look, this is the amount of time and money I have to start off with, where do you think I should invest? I'd say invest in DFAM, invest in design for additive manufacturing. Not every part is 3D printable. Not every part is going to be 3D printable. Not today, not in a decade from now. But to be able to identify, to be able to say, this is where I bring out value, not cost or price, but value. To me, what is value to me is totally different compared to what is value to somebody else. So depending on where I see value or how I can bring out value in it is really the crux of the whole process, where designers can see and they're expected to know and understand that and leverage on it. So manufacturers, we get asked when we do discussions with some of the OEMs and other manufacturers, what do you think we should start with? We say, start investing in DFAM, start investing in training your designers, and preferably the younger ones, because they're a lot more flexible and malleable in terms of learning something new and understanding how they can actually leverage on additive manufacturing and what best aspects they can bring out. Today, very few people do understand lattice structure generations, topology optimization, how you can actually design parts to have better properties or better quality for your entire assembly, lightweighting, yet keeping the strength same or higher. Those aspects of it can be beautifully brought out from 3D printing. Though we see it as applications, we feel it must be some specialized Harvard guy who's doing that. But honestly, there are people who can think. In fact, honestly, we do it as a part of our own jugaad, which if we can look at it, we can combine them and bring out the best in 3D printing. So which we have seen. There are manufacturers today in India who have the early adapters, who have invested that time, effort and money. They've actually seen the true potential from the design stage itself and have started bringing out the best from the technology and started using them. And also, of course, what people should keep in mind is there are different tools. I mean, there are, Mr. Bedi brought out the aspect here beautifully from you have today identified by your software providers who have been adding modules for additive, be it for your die mold tooling design or be it for your medical application. There are a host of software today available from a medical perspective, which will help people design the right kind of part in medical. Aero design today, some of the most exotic software manufacturers, developers have come up with modules for DFAM or design for additive manufacturing. In fact, even Fusion 360 is a very straightforward one. We have Siemens and many others who've done this, developed tools. So understanding, learning, putting that to use to see how before even they go for printing. Printing is a time and a cost consuming exercise, but before that people can do a lot of evaluation to see, can we actually bring out the best in 3D printing? And that is a job of design team and of course the top management's blessing required to do that kind of initiative and take it up, which is the only way we can identify what works right for me, what is the best for my industry, and how we can bring out the best in them. And of course, one of the other aspects is, as I brought out in my previous question, where supports is something that is a challenge. A lot of design for additive manufacturing aspects are taken care. You can use supportless printing or minimum support printing aspects can be beautifully brought out in DFAM itself, design for additive manufacturing. So if you ask me, the extent to which we are actually using is limited because of various reasons here, not only here, even globally. There is a lot of opportunity where designers can try out this. And the ones who have done this, who have explored this and put this to use have reaped a good benefit. And the learnings have been immense for them, which is the real wealth. I mean, there's no textbook which will teach you these aspects. You have to go through the grind, understand these, go tread the real hard way, and then see how you can learn them and treasure them for your own self. So I think that is what I'd like to say from a design perspective and what people are doing globally, and more so in India, where we are, it was mentioned earlier, we are a very risk-averse country. So we do fear failure immensely. We are okay. I mean, my feeling is fail small, but we can grow big if we do that, learn the whole way in the whole process, and then use additive. It's here to stay. I mean, like it or leave it. We can close our eyes and ignore it, but this is here to stay. Don't wait till a customer holds a gun at your head and say, I need it to be done this way. Otherwise, I'm moving it away to somebody else. Invest in the technology, learn the technology, do it through design, and get things printed. It doesn't cost much. It doesn't take too much effort. There are experts in the country who have the ability to help you convert, help you do this progress of migration into this while you still continue doing your own conventional way. So these are my 2 cents worth. Thank you.
Okay, that's very interesting.
Sure.
Thank you.
Very well put. Now I would like to come to my last question, which is for you, Ms. Swati. Now, skills have transformed the industry through the COVID-19 pandemic, and they say that skills are what will bring us out of this pandemic. So, can you say the same for the skills for AM?
2 years back, where every manufacturing unit was shut, we started making face shields and face masks, and then respiratory valve splitters were being prototyped and were being tested with the few hospitals in Bangalore. I was a part of the COVID task force, and when it comes to when there is no money constraint and when there is a low volume of production, obviously it's on demand. 3D printing is on demand. It can instantly do that, right? So that was a phase where we were able to prototype. Being at home, we had a 3D printer at our place. We were able to prototype, right? So I believe there will be a time where things, where we will be able to do a batch production, and then we are building a 3D printing farm where there will be like thousands of printers printing different kind of products. So we are kind of building up the supply chain as well at the same time. So yeah, of course, why not? I would say why not? We did it. We did that in the time of pandemic, where we had no resources at all. Everything was shut. So we did it in a small volume. So why not? When it comes to the other sort of pandemic, we'll be able to sail through it as well. So this as Vishwas rightly said, 3D printing is going to stay for a long period of time. And the beauty of 3D printing is like it keeps on evolving so fast that we feel that we are left behind. Once in a while, new printers with new upgrades, it keeps on coming in the market. And we need to upgrade ourselves in terms of skills as well. So he rightly mentioned that DFAM is the future, of course. The topology optimization, the generative designs, the lattice structures are the future. And these are the skill sets. Obviously, we are going to learn a lot via try and testing these methods. And then obviously we can definitely sail through such pandemics in future as well. God forbid that, of course. Yeah, we won't expect that as well. So yeah, that there is a possibility, of course.
Lovely. Okay, so that will be our panel discussion will be coming to an end now. So that was it. So thank you so much, everyone. Thank you so much, our panelists, for that very, very interesting, very engaging discussion. We had some very practical inputs, and then we had some very, very broad and very, very in-depth ideas about everything. And we had a lot of good insights. So I think this is one of the most interesting panel discussions that I have been a part of. And I thoroughly enjoyed it myself, personally, listening to all of you individually. So thank you so much for that. And thank you very much for joining us once again and for your insightful inputs. So thank you once again. And now I would like to ask Mr. Shekhar Jitkar to please take over and ask you if you have any questions from the audience. Mr. Jitkar, over to you.
Yeah, thanks, Julie. Thanks to all the panelists, each one of you, for taking out time and participating in this panel discussion. It was quite indeed and very enlightening, very informative, and interactive. And thanks to all of you for sharing your views, whatever information you have, honestly and openly. And it will definitely, I think, more and more such events will happen, and definitely people will get the realization of the usage of 3D printing or additive manufacturing in future, how it can be beneficial and how we can then India can compete with the Western world in terms of adopting the new technologies. We are still behind, as many people mentioned, we are still much behind the Western world. But I think in a given time, the opportunities and potential which the technology has, we will be able to catch up with other countries in terms of adopting the 3D technologies. So currently, I feel since we are running short of time, so we will not take the questions. So whatever questions we'll get, we'll maybe try to answer offline. So I think we'll conclude the session here. And once again, thanks to all of you. It was really great. It was pleasure having all of you in this today's session. And over to you, Julie, just a concluding remarks.
Thank you.
Thank you, Mr. Jitkar. Thank you, panelists.
Sure.
So
Thank you.
Thank you, ladies and gentlemen, for joining us today. We'll now be coming to the close of our summit. So the summit told us a lot about 3D printing today, which I'm sure all of you can go back and apply on your shop floors and in your factories. And we talked about all the practical solutions that we can implement. So it was a very great summit for me. So before we close, I would like to thank our wonderful audience for being a part of today's summit. I would also like to thank our ever presenters, speakers, and panelists, and our technology partners, Autodesk Fusion 360 and Philips. I would also like to thank Dr. L. Jyotish Kumar and AMSI for joining us as our association partner. So thank you all very much, and we'll see you next time.